Welcome, everyone, to ICFP 2026 and to Indianapolis and Indiana University. I first want to thank everyone at the Luddy School of Informatics, Computing, and Engineering and at IU Indianapolis for their work to make this possible. I also want to thank our generous sponsors who are part of what makes it possible for us to put on this amazing event and to provide the support for everyone that makes our ICFP community great. So thank you to our sponsors. Tonight, after the sessions, we will have a poster reception in the auditorium lobby and hallway that you were just in. That will feature posters from the SRC program, our sponsors, and a bar and snacks. Also tonight is the Women in PL dinner at the Ratskeller, which is about a 30-minute walk from here. Paulette, our student volunteer co-chair, will be walking over starting at 7 from the reception. So if the Women's in PL dinner is for you, then we encourage you to attend that and walk over with Paulette. And with that, I invite you all to enjoy a fantastic program of ICFP. And to introduce our first speaker is our program chair, Manuel Serrano.
So hi, everybody. It's my pleasure to introduce Edward Lee, which has been working on embedded system and software for 40 years at Yale, MIT, Bell Labs, and at Berkeley, where he is now Distinguished Professor Emeritus in Electrical Engineering in Computer Science. His research is focused on cyber-physical systems, where he strives to make composable, secure, and verifiable timing-sensitive systems. Edward Lee's work emphasizes deterministic models to address unpredictability in distributed systems, particularly for real-time applications. He led the Ptolemy project that aimed at modeling, simulating, and designing concurrent real-time embedded systems with a focus on assembling concurrent components. The key underlying principle in the use of well-defined models of computation that govern a coordination language that use logical time, the key underlying principle is the use of a well-defined models of computation that governs the interaction between components. He also developed lingua franca, a coordination language that uses logical timestamp to ensure determinism in distributed environments. As you may have understood now, Edward is not, strictly speaking, a PL person, and maybe even less an FL person. However, we have a lot of common. We work on similar problems, namely programming distributed systems, and share a similar approach with a strong theoretical background and emphasize on compositionality and a preference for determinism whenever possible. We therefore felt that Edward could bring a slightly different perspective from what we are used to, one that could be particularly enlightening for our community. So, Edward.
Thank you, Manuel. All right. Thank you, Manuel, and thank you all for being here, and thank you for inviting me. As Manuel explained, I'm not really a programming languages person or a functional programming person. In fact, my context is cyber-physical systems, so simple way to summarize that is that I'm really only interested in computers when they interact with the physical world. I am told that there are people who are interested in computers that do not interact with the physical world, but I'm not one of those. So now, when we talk about deterministic models, that's going to be my focus today. And in this context, deterministic models can certainly play a pretty major role, right? On each of the computational platforms, we're pretty used to using deterministic models. The design of the hardware is based on synchronous digital logic, which is a deterministic model. Single-threaded imperative programs provide you with a deterministic model. Functional programs provide you with a deterministic model. In the network, we even use deterministic models. So the abstraction behind TCP/IP, reliable in-order delivery, for example, gives you a deterministic model. When you talk about physical plants, we also tend to use deterministic models quite a lot. Ordinary differential equations, for example, are deterministic models for the behavior of some physical plant. Now, when you put all these things together and you start having computers interacting over networks and interacting with the physical world, things tend to break down, right? And you compose these deterministic models and you don't actually get a deterministic model because basically these models are working in largely independent worlds. And when you put them together, you lose this determinism. Now, what do I mean by deterministic concurrency? If you look at a lot of the early literature in computer science, you would come to the conclusion that deterministic concurrency is an oxymoron, because in fact, concurrency is often defined in terms of non-determinism. So non-deterministic interleaving of atomic operations, for example, is a very common definition of concurrency. Non-determinism itself is often defined as exhibiting observably different behavior given the same inputs. Both of these definitions are actually seriously problematic. So I'd like to give you a couple of examples. So let's just look at a simple single-threaded imperative program. This is a program that computes a Fibonacci sequence. So simple question, is this program deterministic? Well, if you define determinism as, if you define non-determinism as exhibiting observably different behavior given the same inputs, well, this program has only one input. It's the number of Fibonacci numbers you want to produce. So is this deterministic? Well, it depends on what you mean by observable behavior. For example, if the time at which an output is printed is observable, is it observable? Well, generally, yes. So under that definition, every program is non-deterministic. So that actually doesn't give us a useful definition of non-determinism. So we're going to have to refine that definition a bit. Now, let me give you, there's no concurrency in this, but let me give you a concurrent example. So here's a very simple system that involves three processes, C1, C2, C3. C1 dispatches a request to C2 and C3, and C2 very simply produces a sequence, AB, okay? It'll print those out, for example. And C3 produces a sequence, CD, okay? So is this deterministic? Well, it very much depends, again, on what you mean by observable behavior. If you're printing these sequences to the same console, you might observe any of 6 possible interleavings of these output sequences, in which case you would come to the conclusion that this is a non-deterministic program. On the other hand, if you define the observable behavior as a pair of sequences, this is a perfectly deterministic program. Okay, so it makes a big difference how you define observable behavior, and it makes a big difference also how you define inputs. So my essential claim is that determinism is not, in fact, a property of any physical realization of a system. That's not a useful way to think of determinism. Determinism is a property of a model of a system. And you can define determinism as a property of a model in a very straightforward way. A model is deterministic if, given some initial state and given the inputs, the model defines exactly one behavior. Now, in order to make that definition rigorous, you have to define what you mean by state, what you mean by inputs, and what you mean by behavior. And if you don't define those, you don't actually have any way of resolving whether your model is deterministic. Okay? So let me focus on this issue of models versus physical systems. Well, most of us have learned to use models in the context of scientific work, right? And in science, the value of a model lies in how well its behavior matches that of a physical system. That's, I think, a statement that I would be very surprised if anyone in this room would disagree with. But in engineering, we actually use models in a rather different way, okay? In engineering, the value of a physical system lies in how well its behavior matches that of a model, okay? If I give you a piece of silicon and it doesn't behave according to the instruction set architecture model, it's not a useful piece of silicon. It's the silicon that is flawed, not the model, okay? So these are very complementary uses of models. So another way to think about this is, a scientist asks, can I make a model for this thing? And an engineer asks, can I make a thing for this model? All right? Similarly, a scientist says, all models are wrong, but some are useful. An engineer says, all implementations are wrong, but some are useful. No implementation will conform perfectly with a model. All right? Any piece of silicon that I give you that implements some instruction set architecture can deviate from that model if the chip overheats, for example, or you immerse it in salt water, or something goes wrong. Things go wrong. So any physical realization of a system is in fact going to be imperfect and will never perfectly match a model. So going back to this Fibonacci sequence calculator, right? The program here is a model, and it's an engineering model. It's a specification of how we want the system to behave. And if we define the output, and if we define the input as the number provided to the program, and the output as the sequence of numbers that is produced, that sequence of numbers becomes the behavior, and now we do in fact have a deterministic model. And it's not about what's observable to a human, okay? It's about what is defined to be observable within the context of the model. So in the context of these cyber-physical systems where we're combining deterministic models, programs running on nodes, interacting over networks, interacting through the physical world, if we ask the question about whether deterministic models are useful, the scientific approach would say, well, is a deterministic model a faithful realization of that system? And the answer is almost certainly going to be no, sorry, it's hopeless. But my claim is that that's the wrong question, okay? The right question is whether we can build cyber-physical systems whose behavior matches that of a deterministic model with high confidence, right? No physical realization is ever perfect. So let me give you a situation in which I feel like there's a whole community that's been doing things wrong, the real-time systems community, okay? So real-time systems software people focus on trying to determine what the worst-case execution time is of some piece of software. Well, the question of what the worst-case execution time is doesn't even make sense until you map it onto a particular piece of hardware. It's not enough to know that what the instruction set architecture is. You have to know what the hardware is, what the memory architecture is, how much memory there is, what is the cache protocol. You need to know everything about that physical realization before you can even talk about worst-case execution times. And then you're constructing a scientific model of that physical realization and trying to draw conclusions about the design from that. I think that's an entirely backwards way to approach real-time systems. And in our work, we approach it from the reverse direction, from an engineering direction. We specify programs that give specifications of what the real-time behavior should be, and then our job is to engineer the physical realization to deliver that real-time behavior. Okay, it turns the problem around completely. Now, There's a lot of advantages to deterministic models. I mean, the whole scaffolding of computing depends on deterministic models, right? Where would we be without synchronous digital logic? Think about that. There's enormous advantages to deterministic models. They're, of course, more predictable. Known inputs give you known behavior. Testing is more useful, right? You can do regression testing because given the inputs, there's one correct answer, so you can check to see whether you get that answer as your system evolves. Analysis is more tractable. It's easier to use math, Boolean algebra, calculus, etc. Simulation is more useful, right? You give it an input, the behavior that you observe in the simulation is going to be the behavior that you're going to get. Verification scales better because your state space is a lot smaller. Detecting faults is easier because you have a well-defined notion of what a correct behavior is. How do you detect faults if you don't know what correct behavior is? Now, none of this says that non-deterministic models are useless. That's not my claim. There are enormous uses for non-deterministic models, right? They're a useful abstraction technique. They're useful for handling uncertainty. They're useful for deferring design decisions. There's lots of uses for non-deterministic models, but they're very complementary uses. And often these things get conflated. Now, deterministic concurrency is actually not a new topic, right? Gilles Kahn in the 1970s was working on process networks, which are distributed systems that give you deterministic behavior. Data flow models in the 1970s, synchronous languages from the 1980s, discrete event systems, logical execution time in the 2000s, and most recently, reactors, which are my focus these days. So this is an old topic, and yet when you look at concurrent systems today, non-deterministic models are everywhere. It's almost all concurrent programs and all distributed programs use non-deterministic models. They use things like shared memory, of course, threads. Threads are horrifically non-deterministic, and the challenge of a programmer writing multi-threaded programs is to try to rein in that non-determinism by imposing constraints on the execution. Publish and subscribe techniques like the data distribution service or the robotic operating system, ROS. Publish and subscribe is used in safety critical systems, and it has undefined behavior for most distributed applications. MQTT is used in Internet of Things applications. And in cloud computing, Azure and Google Cloud are using publish and subscribe. And these are non-deterministic frameworks. Actor models, like used in Akka and Erlang and Orleans and Rebecca and Scala. Service-oriented architectures like remote procedure calls, Bond and Thrift. These are all, in fact, non-deterministic concurrent models. And they define the bread and butter of how things are done today. I'd like to convince you today that there is a better way, okay? And I've been focused on this model of computation that we call reactors. And it's been under development as a kind of international collaboration, mostly Germans and Americans involved so far, but a few other scattered people around the world. And the objective here is deterministic concurrency. And I'm going to focus on the first full-scale realization of this, which is in a coordination language called lingua franca. So let me explain the reactor model to begin with. All right, so a reactor is a software component that maintains local state. Okay, so you can think of it just like in object-oriented programming, this is an object. Okay, it maintains local state, but it also has local events. These events can be periodic, they can be scheduled, they can be asynchronous. There's a notion of logical time in this system, which is kind of the fabric that binds the system together. It need not necessarily have a strong connection with physical time, but it is often very useful to bind it to physical time. I'll give some examples of that. Okay. There's a local physical clock that enables that binding with physical time, but we don't have any illusions about physical clocks being perfectly synchronized across a distributed system. They're not. They never are. They can't be, in fact. It's physically impossible. Reactors have input ports. They receive events, time-stamped events. And the goal is for them to process events in timestamp order. And instead of methods, as you would find in object-oriented program, we have reactions. And reactions are triggered by events, and they produce new events. And those new events get sent to output ports, which are used to communicate with other reactors. So this is the essential model under the reactor model of computation. And the goal is that for each reactor to process events in timestamp order. Okay, and I'm going to show you that when you compose these things, you get deterministic models, deterministic concurrent models, and I'm going to show you that these deterministic models perform very competitively with the non-deterministic techniques that are widely used. So let me zero in on an example, okay, of a reactor program. And I'm gonna go PowerPointless for a minute, and I think, let me make sure this will work. So yes, good, you can see this. So this is the lingua franca program, and lingua franca is a coordination language. And so these diagrams that I am showing, that show up on my PowerPoint slides, are all actually automatically generated. So here we have a main reactor, a top-level reactor called the reflex game, that instantiates three components: a random source, a get user input, and a user component, and then connects them together. Okay, and to prove that this is live, we can create another instance, for example, of this random source, and the diagram updates. I can go and connect this to, this is like so, and the diagram rewires, okay? So you instantiate the components, you interconnect them, and these are conceptually concurrent. There's dependencies, of course, so the concurrency is restricted by the dependencies. When one reaction produces an event that is consumed by another reaction, there's a dependence there, that will be respected. But when there are reactions that do not have dependencies across them, they can execute concurrently, and they can execute on separate machines and communicate through networks. So let me undo these changes and go back to the original program. And this program was inspired by a simple test case that is often used to introduce synchronous languages. It's called the reflex game, okay? And it's a simple game program that just is measuring the reflex time of a user. So the way that it works is that there is this user component which simply listens for keyboard inputs and then timestamps the keyboard input, okay? And the random source produces a stimulus to the user that says, okay, you should hit the keyboard now, and then the get user input measures the time difference between the production of the prompt and the response of the user, okay? So it's just measuring your reflex time. So I can run this program. If I click here, it'll build the program and then start executing it. Okay, it gives me some instructions. It says watch for the prompt, then hit return or enter. Type Control D to quit. Okay, so it said hit return or enter. Whoops, I'm in the wrong window here. It took me 11 seconds. My reflexes are not very good. Let's try to do better. Okay, 3.9 seconds. Not so great. Maybe I can do better. Half a second. That's much better. Let me try to go even. Oh, geez, I cheated. I hit return before it prompted me, and so then the program gives me the average response time and exits. Okay. All right. So this is an example of a program that is interacting with the physical world, so it's a cyber-physical system, okay? It's using timing as sort of an integral part of how it's working with the physical world. And yeah, so let's look at the question now. Is this a deterministic program? What do you think? Kind of depends on how you define inputs and how you define behavior, right? So let's look at this fairly closely, all right? So my claim is that if you define inputs and behavior appropriately, this program is deterministic. And in particular, the way that I'm going to define it is that the timestamps assigned to the user's response on the keyboard will be considered input. Okay? The random number generator, the seed used for the random number generator, will be considered input. Under that definition of input, then there is a definition of behavior where this program is perfectly deterministic. And that definition of behavior is the signals communicated on each of these communication paths. Okay? Each of these communication paths between components carries a sequence of time-stamped events. And with this composition, that sequence of time-stamped events will be a deterministic function of the inputs in the way that I've defined the inputs. Okay? So from that perspective, the model in this case is deterministic, where I've appropriately defined the behavior. And consequently, I can treat this program as a deterministic specification that I want to then realize in a physical realization on my laptop, right? And the way that that works is that the lingua franca compiler, it's a coordination language, so it produces a program in whatever target language you choose. In this case, I think the example that I gave was using C. So each reaction was defined in C. The lingua franca compiler puts together the whole program, which can be distributed, so it can be distributed across processes, across networks, and generates the appropriate programs in the target language. You compile those into an instruction set architecture, and you run those on the physical thing. And the idea is that that physical thing will, with high confidence, behave like the deterministic model. So this is a conference on functional programming. So I'd like to give you a functional programming interpretation of this, okay? And it's going to be a slightly bizarre one because it's not going to look very much like Haskell or SML, all right? So first of all, the inputs and outputs to these components are signals, which I can define formally as functions that map a tag set into a value set, which is a data type, okay, or absent. Okay, so at any given tag, which can be a timestamp, but tags are more general than timestamps. At any given tag, you either get a data value or nothing. Okay, so you could sketch a signal, which is a communication between the components, by the tag set is required to be totally ordered. Okay, so you put the tags along a line, and you have events which have values, and in between events that have values, you have absent. All right, so those are signals. So a reactor then can be defined as a function that maps an M tuple of signals into an N tuple of signals. Okay, it can have any number of input ports, including 0 input ports, and any number of output ports, including 0. And you can model it as a function that maps input signals to output signals. So what does that look like in terms of this reflex game? Well, the user component has no input ports, okay? So we model it as a function f sub u that maps a 0 tuple. Well, what is that, s to the 0? Well, in set theory, that's a very common usage. That's simply a singleton set. Okay, it's a set with exactly one element. It doesn't matter what that element is, but it only has one element. all right? And the output is a single signal, so that's S to the 1, okay? And so the user component is modeled as a function that takes a singleton and produces a signal as an output. That conforms with the verbal description that I gave you. If you consider as input to the system the timestamps assigned to when I hit return, okay, then I can model this as a function that produces that sequence of events with those timestamps, okay? It's a perfectly deterministic function. It's a function of a singleton set, so it always produces the same output, all right? And it is a deterministic function. The get user input has two input ports, so it maps a pair of input sequences, of input signals to a single output signal. And the random source has one input port and one output port, so it just maps an input signal to an output signal. Okay, and once again, in order to define this as a function, I'm going to have to provide as input the seed to the random number generator, okay, which produces this random delay. And once I've got that seed, I can define that function. Okay, so I can define each of these as functions that map tuples of signals into tuples of signals, with using care to define what we mean by input, and the input is what affects the definition of these functions. Okay, so now I take this structure of this reflex game, I can abstract it like this. It's a network of three components. There are three signals involved, which are the signals that are the communication between the components. Let me just rearrange that diagram, okay? So I just take the components, stack them up, draw a little yellow box around them, and suddenly I realize that actually the whole system can be modeled as a single function that maps a three-tuple of signals into a three-tuple of signals, which means that I am actually looking for a three-tuple of signals that is a fixed point of a function. Okay? The input and the output need to be identical in this case. So any network of reactors can be modeled as a single endo function. Endo function just means the domain and the codomain are the same. Okay? So any network of reactors can be modeled as an endo function of the form that maps an n-tuple of signals into an n-tuple of signals, and its behavior is a fixed point. Now, the determinism question becomes a simple mathematical question. Does the fixed point exist, and is it unique? Okay? So what do we do when we're looking for fixed points? Well, one of the classic results for looking for fixed points and uniqueness of fixed points is the Banach fixed point theorem. So the Banach fixed point theorem says a delta contracting function, endo function, on a complete metric space has a unique fixed point, and it gives, in fact, a constructive procedure for finding that fixed point. You start with an arbitrary signal, and you apply the function, and then you apply the function to the result, and you keep doing that. And this sequence can be shown then to converge to a unique fixed point of that function, okay? But you have to have a delta contracting function, and you have to have a complete metric space. Do we have that? Well, it turns out that we do sometimes, okay? Now, I'm gonna share with you something that I first learned in 1994 from Gérard Berry when I was on sabbatical at INRIA in France, and it changed my life, okay? It's one of the most incredibly cool things I've ever seen, and so I hope you'll find it equally cool. It's called the Cantor metric, okay? So the Cantor metric says that the distance between two signals is 2 to the minus tau, where tau is loosely, because there's some mathematical trickiness, but it's loosely the earliest time at which the two signals differ, okay? So if I have a signal, which is a sequence of time-stamped events, and another signal that is a sequence of time-stamped events, and the two are identical until some time tau where they differ, okay? In this particular case, S1 has an event where S2 does not, okay? So at that tau, they differ, then I can define a distance between these two signals to be 2 to the minus tau, all right? So how does this work as a distance from a metric perspective? Well, if two signals are identical, what is tau? Well, the earliest time at which they differ is infinite, okay? So 2 to the minus infinity is 0. So two identical signals have a 0 distance between them. That's what you want from a metric, right? If your timestamps have an origin of 0 and the two signals differ right at 0, then 2 to the minus 0 is 1, okay? So in this particular metric, two signals have a distance between them that is always 0, between 0 and 1, some real number between 0 and 1, okay? So how do we use this? Well, so it turns out that for discrete event signals, we actually can show that we get a complete metric space with this. And there is some mathematical trickiness in this, but you can go to the references and work out these mathematical differences, but you can show that you do get a complete metric space. By the way, I should mention this for discrete event signals, caveat, is kind of interesting. I mean, one of the things that gets excluded, for example, in this caveat is Zeno signals, where you have an infinite number of events and then some more events, okay? Those turn out to break this complete metric space, but in a way that we can resolve. I'll get to that. Okay. Now, what can we do with this metric? Well, one immediate thing that we can do is we can come up with a mathematical definition of causality. Okay, causality is loosely, the outputs can only depend on the inputs. Okay, but in this time-stamped world, it's a little more constrained. The outputs should not depend on future inputs. Okay, they can only depend on the inputs that you've received up to a certain time. So an output with a certain timestamp should depend only on time-stamped inputs with lesser or equal timestamps. Well, in the Cantor metric, that just means that the distance between two possible input signals should be bigger than the distance between the two possible output signals. Okay? Because of this is 2 to the minus tau, if you think of it as the time at which the two signals differ, the inequalities reverse. All right, so what this says is that the time at which two inputs differ should be no bigger than the time at which two outputs differ. Did I get the polarity right? Okay, good. So that now you can talk about a causal system where the inequality is not strict. You can talk about a strictly causal system where the inequality is strict. And you can talk about a delta causal system where there is at least some delta time delay between the input and the output. And the Banach fixed point theorem, it turns out, depends on that delta causality, okay, which is why Zeno systems get excluded. So reactors are causal by construction, but not delta causal, okay? So how does this work? Well, let's look specifically at this reflex game example. What about the user, right? The user input is a singleton set. So the distance between two inputs is always 0 because it's a singleton set. There's only one possible input to the function. As a consequence, the user component is delta causal with delta equals 0. All right, very simple case. The get user input, however, given an event on this input, it produces an instantaneous identical timestamp event on this output, so it is only causal. The random source, if you assume that there's a lower bound on the delay that it produces, will be delta causal, and in the particular program that I showed you, there is a lower bound of 2 seconds. it always delays the next prompt by at least 2 seconds. So that gives us a delta causal component. Okay? If we construct this single fixed point problem using these causal and delta causal systems, we discover that this function f is causal, but not strictly causal nor delta causal. And as a consequence, we cannot immediately apply the Banach fixed point theorem. Now, there's a little technicality, right? The Banach fixed point theorem talked about a delta contraction, not a delta causal. What's the difference? Well, the only difference is that a contraction talks about an endo function, whereas causal is any function mapping tuples to tuples, but the tuples don't have to match, okay? But that's really the only difference. It's still a delta contraction is a delta causal function. It just happens to be an endo function. Okay, so reactor systems are contractions by construction, but not delta contractions. However, for this particular fixed point problem, it turns out that if you simply take our function and compose it with itself twice, the composition is delta causal, okay? One way to see that is that on any path from an input to the output of the composition, there is a routing through a time delay, okay? So you just compose this with itself twice, and you get a delta contraction, and you can immediately apply the Banach fixed point theorem. And then in this, I'm working on this, this book that is almost finished. You can go to my website to see the current draft. ACM has agreed to publish this book. I'm under contract to deliver it in September. And it develops all of the math behind this, okay? And in it, there's this proposition that if F is eventually delta contracting for some E, which means that F to the E is a delta contraction, and then you can use the Banach fixed point theorem to find a fixed point of F to the E, and you can prove that that fixed point of F to the E is also a fixed point of F. All right? So as a consequence, as long as you've got a non-zero delay on every path in every cycle of the system, here's the summary of the statement, every reactor system where every directed loop connecting reactions has at least one logical delay with a lower bound on the delay, such a system is always eventually delta contracting, and as a consequence, every such system is deterministic, and the Banach fixed point theorem gives you a constructive procedure for finding its behavior. Now, the requirement for a delta delay is overly constraining, okay? For many systems, particularly systems where you don't actually care about real time, you don't want to have this delta delay. That's, wait, what do you mean? I don't care about real time. Well, it turns out you can generalize the Banach fixed point theorem. We can construct a generalized ultrametric space, and this is pretty wild, okay? But bear with me, okay? It says, it defines the distance between two signals as a set rather than a number, okay? And it's the largest down set, which is a set that includes everything lower than it, and these are tags, so that's a totally ordered set. So it's the largest down set over which the two signals are identical. And then you define the distance. The distance is simply that set, okay? You can show now that with this distance, you get not only a metric space, but actually an ultrametric space, which is a stronger form. You can also define a prefix order on these signals, and then you can generalize the Banach fixed point theorem and get a new constructive fixed point theorem in this generalized ultrametric space. And I'm not going to go through the math, but I do want to credit this theorem was developed by a very brilliant PhD student of mine, Eleftherios Matsikoudis. So I call this the Matsikoudis fixed point theorem. which he published back in 2015. And it's actually more interesting than the Banach fixed point theorem, because the Banach fixed point theorem has a key weakness when it comes to actually using it in practice, right? The constructive procedure that it gives, each time you apply this function, you are actually working on infinite data structures, potentially infinite data structures, because each function maps a potentially infinite input sequence with potentially infinite number of events into a potentially infinite sequence of events on the output. And so each application in the constructive procedure is working with infinite objects, which is practically impractical. The Matsukuda's fixed point theorem gives a constructive procedure that incrementally constructs the signals step by step using always finite objects. Okay, so it's actually an implementable constructive procedure as opposed to the Banach fixed point theorem, which is not actually implementable. We can show that every functional reactor system that is free of causality loops is eventually strictly contracting and has a unique fixed point that can be found via a possibly transfinite constructive procedure. The transfinite constructive procedure deals with Zeno systems. Okay, so this constructive procedure can actually deal with an infinite number of events followed by some more events. It works out mathematically. Now, what about this caveat of causality loops? Well, causality loops, it turns out, are simply situations where the execution of a reaction depends on itself. And those are detected by the lingua franca compiler and rejected. And the way that it's rejected is it just shows up in the diagram like this, and it shows you where your causality loop is, and you have to fix it. Okay, there's no way to realize this program because the execution of a reaction cannot occur until the execution of the reaction has already occurred. And so every program that is free of such causality loops gives us a strictly contracting function, and consequently every composition of reactors will give us a deterministic behavior. So in practice, we use this in lingua franca to build programs that vary over a wide variety of different platforms. We map programs onto embedded processors with microkernels like Riot or Zephyr or even bare metal. We map them onto laptops, which is very convenient for development. We map them onto data center virtual machines in data centers. And more interestingly, we map them onto systems that distribute across these platforms. So we can have an embedded component, a edge component, and a cloud component. And the composition of these components is defined as a composition of reactors, which is by construction deterministic. Now, a lot of people say, well, this determinism must come at a performance cost. It doesn't, okay? It really doesn't. And we have a paper here where we prove this, okay? We show with lingua franca that we took a set of benchmarks for actor systems, which have very similar structures to reactor systems, and we re-implemented all the benchmarks using reactors, and our behavior was, in many cases, better than the actor system implementation, and in all cases comparable. You can compare us against publish and subscribe systems. So we published a paper in this robotics conference last year, which showed we took a self-driving car scenario, and using reactors, we run approximately 10 times faster than something based on the pub-sub framework of ROS, which is the widely used standard used in this world. And ROS, being non-deterministic, we published a paper that took a widely used self-driving car open source stack called AutoWare, and showed that the non-determinism due to the publish and subscribe framework could lead to some very treacherous situations in this self-driving car scenario. In particular, it could lead to mode confusion, where the car would be would think it was moving forward but was actually in reverse gear, or would think it was moving in reverse but was actually in forward gear, and those scenarios would arise simply because of the non-determinism in the pub/sub framework and not because of any intrinsic problem in the system. And we also showed, in this case, that those scenarios showed up extremely rarely in testing, which is worse than showing up more frequently in testing, okay? Because you're unlikely to see them in testing. You're going to see them only once you've deployed this into cars on the road, which is very problematic. Is this system scalable? Well, it turns out that the underlying technique behind the distributed systems that we use, the way that we implement the distributed systems, which is we published way back in 2007, but the technique was independently reinvented at Google and was made the backbone of Google Spanner, which is probably the world's largest distributed database. So the technique has been shown to scale to planetary scales, and as a consequence, scalability is not fundamentally a problem. So the reactor model of computation in particular has a few realizations these days. The example that I showed you is this lingua franca program. We have a variant of this that we call micro-LF that is targeted specifically to embedded processors. There's a commercial version maintained and developed by a startup company called Kronos. And there's an experimental version that is still very early stage, but our goal with this is to replace ROS and to replace the non-deterministic mechanisms used in robotic systems. So, in conclusion, my claim is that determinism is an extremely valuable property of engineering models. Don't confuse that with scientific models. They have a different role. They have a completely different function in design. Models with deterministic concurrency have been around for decades, but non-deterministic concurrency still dominates in practice. I'm trying to fix that, along with all of my partners on this project. And I think reactors are a very promising approach. So thank you very much. So I think we have some time for questions.
Yes, we do. So please come to the microphone if you do have questions.
So first of all, really enjoyable. I like the emphasis on connecting this with the historical research. But if I was going to engineer this in a practical system today, what are the key features that I'm looking for that are necessary to implement? Is this, you just make sure that you've got time-stamped events and your processes are handling events in time-stamped order and things are modeled as event systems? Is that all that's necessary to get these benefits, or is there more to it?
That really is, I mean, at one level, that is all that's necessary, right? It requires rethinking your system design in terms of components that exchange events. There are some fundamental trade-offs that you have to worry about, right? Particularly in distributed systems where latencies can be highly variable in the communication, and that will have consequences. And there are some fundamental trade-offs that you have to work with. We have, in fact, been working on mechanisms to help you navigate that trade-off. In fact, we have a generalization of Brewer's CAP theorem that we call the CAL theorem, which is a very convenient acronym because CAL is what Berkeley is known as to locals in California. But it stands for consistency, availability, and latency. And it gives a quantified relationship between these three and shows you how to work the trade-off. As your network latencies increase, what are the consequences on system design? And we're integrating this with lingua franca so that you can use the structure of your program to actually analyze these trade-offs and work the trade-offs.
I think that partially answers my question. I've heard of the notion of causal ordering in the context of a partial order, and I'm guessing you have a time stamping mechanism that does totally order all of these events between reactors, correct? And so then that causes availability problems.
Well, the availability problems are more fundamental, right? They're simply a consequence of communication latencies. And the total ordering, one of the challenges that we constantly have with this framework, and that requires a little bit of a mind bend to think about it, is that there's never only one timeline. And it's actually rather difficult in natural language to form sentences that talk about multiple timelines at the same time. Because our natural language, I think, is intrinsically bound with having a single timeline. But the logical timeline of the timestamps and the physical time of your executions are two different things, and they're very malleable with respect to one another. So when you think of partial orders, a lingua franca program, even though the timestamps are totally ordered, actually executes in a highly partially ordered way. Right? The dependencies between time-stamped events constrain the physical times at which things can occur. But those are only constraints, right? The actual physical times at which they occur are partially ordered. This is how you get concurrency. So it's a mistake to think of the fact that you have a totally ordered tag set as meaning that everything in the system is totally ordered. It's not, far from it.
Right, so if I have a reactor that sends, so A sends events to B and C, and then B and C send events to D. So if C sends the event first, D will have to wait until B has finished sending its event. How would we enforce that?
Well, how you enforce it is a big part of the trickiness in how you implement the lingua franca system, and that's a whole different talk. You can go and look at the papers to see how we actually implement it. The technique that I am most enthusiastic about these days is also the one that is used by Google Spanner.
Hi, great talk. So I have a question. Currently real-time systems, the biggest problem is certification, and the way it's currently approached is, as you said, WCET analysis, which is kind of observing how these systems behave in their intended environment of operation, right? So how do deterministic models, one, help with certification? Two, would certifying a model mean that the system that it builds is also certified, or would you still need to do like a WCET kind of analysis?
Yeah, that's an excellent question. And I think one of the key challenges there is making sure to not confuse the map and the territory, right? Certification can never be about a physical realization. That simply doesn't make any sense, right? Can you certify that this particular piece of silicon will always behave in this particular way? No, nobody can do that, right? So once you recognize that certification is always about a model, okay, that changes the question. And I think that the use of deterministic models could greatly facilitate certification given that recognition.
Hi, Max New, University of Michigan. So I'm not sure if you're aware of this, but this idea of metric space-based semantics has really developed on the PL side and now is very common as a foundation for things like separation logic, which is used for a lot of verification. And from the PL perspective, one of the issues that we have with this kind of semantics is it's very sensitive to things like the actual time steps, and small changes to a program that might change exact timings mean that the programs are no longer equivalent, right? And so in PL, what we're trying to prove a lot is I did this refactor and I get a very similar system, right? Or an equivalent system. And we want to prove things like by simulations of these systems where they don't have the exact same timing, but we want to say they're equivalent in some way. So I'm just wondering if this is a kind of problem that you're encountering in your area and what kind of techniques you use to deal with it.
So I've seen quite a bit of that work, and one of the things that I've seen is a refusal to use multiple timelines. And so when people talk about timing, they're usually talking about physical timing, and then of course, you get tremendous sensitivity. In fact, physical timing in a distributed system is extremely problematic because you don't have a common notion of time across a distributed system. I think that the thing that is missing there is the separation between logical time and physical time. And when you separate these two, you can create systems that are perfectly deterministic in extremely robust ways. And I think that that's the thing that I've seen missing in some of that literature, is that this inability to separate these timelines.
Okay, thank you.
My question is very much along related lines. So Google's Spanner is actually built on this very cool system they have for having very accurate and synchronized physical time. Of course, as you've pointed out, it's not possible to have perfectly synchronized physical time, but they do pretty well. And then they have an interesting protocol for bounding distance away from that time. So can you say something about the connection between those kinds, that kind of system and the work that you're doing here with multiple logical timelines?
Yeah, excellent question again. And so one of the things that we have shown in this Cal theorem context is that clock synchronization error is indistinguishable from network latency. Okay, you can't actually separate the two. Fundamentally, this is actually true from basic principles in physics. In physics, it's actually impossible to measure a one-way latency. Okay, you can measure a round-trip latency, but you can't measure a one-way latency. And a big part of the reason for that is that you don't have a common notion of time at the two ends. Okay, so latency and clock synchronization error cannot be separated. The reason that Spanner uses tightly synchronized clocks is that they want good availability. They want to bound the amount of time that a replica of the database takes to respond to a query about what the value of a record is. Okay, as soon as you want to bound that availability, okay, you have a timing constraint, you have a cyber-physical system now, and your ability to bound that availability depends on network latencies and on clock synchronization error, and the two are tied together. They can't be separated. Okay, so Spanner also uses dedicated trunks to reduce the network latency between their data centers that replicate the database. Okay, and the issue here is that the latency and clock synchronization error together give you a fundamental bound on availability. If you don't care about availability, you don't need synchronized clocks, and you don't need bounds on network latency. So if you're not dealing with a cyber-physical system, if your system doesn't interact with the physical world, you don't need to synchronize clocks. It's completely unnecessary. Okay? But as soon as you care about the timing of the interaction with the physical world, well, then latency and clock synchronization will come into play.
Hello, my question is about the network topology. So in your examples, it seems that the topology is fixed. But for publish and subscribe, for example, the benefit is you can add more subscribers and remove subscribers dynamically. So how do you deal with this? And also, in distributed system, you want things to independently fail, but also not fail the entire system. So do you have ways to deal with this with lingua franca?
Very, very good question. And so the reactor model does fundamentally support mutations. Depending on how you implement it, it can be quite costly, okay? Because the reactor model does depend on being able to analyze dependencies. And if your dependencies change dynamically, then you have to reanalyze the dependencies when they change. Okay, so there can be a cost to supporting it. We've shown that there's a lot of very practical special cases where we can greatly reduce the cost of supporting mutating structures, right? But there's going to be a cost. And there was a second part to your question, but I can't remember what it was.
It's about failures in distributed
Oh, yeah,
systems.
failures. Okay. So fault tolerance is a big issue that we've addressed. And I think one of the key things is that when you talk about deterministic models, right, the model is deterministic. A model, an implementation of a model is deterministic only under certain assumptions, okay? If I give you an instruction set architecture, that gives you a deterministic model, right? Is a piece of silicon a faithful realization of it? Well, yes, but only under certain assumptions. The clock rate is bounded by a certain amount, the temperature is bounded by a certain amount. If any of those assumptions get violated, then you get a fault, right? We treat faults as deviations from the specified deterministic behavior. Having a deterministic model enables detecting those faults. If you have a pub-sub system, for example, you may not be able to detect faults, right? If you're subscribed to something and you don't receive anything, when do you declare a fault? How do you know that a fault has occurred? How do you know that the publisher isn't there anymore? There's nothing in the semantics of pub-sub that helps you do that. There's no sound basis for determining the existence of a fault. On the other hand, if you have a deterministic model, we have shown you can detect faults instantly. If you're expecting a response by a certain time, and that time elapses and you haven't gotten a response, bingo, you've declared a fault. You can react to that fault. And lingua franca includes in the language these fault handlers and mechanisms for detecting those faults.
Hi. My question would be, maybe it reflects my misunderstanding, but could you show an example for a fixed point? So, for example, for the reflex gain?
Yeah, the fixed point is, you know, when I ran the program, right, there was a sequence of time-stamped events that was exchanged between these components. It was a finite sequence because I cheated. If I didn't cheat, it could go on forever, right? But that is a fixed point of the composition of the functions.
Thank you.
Okay, thank you very much. Okay, so we have a coffee break and snacks in the lobby just next to the door.
Okay.
Thank you. All right, everyone, welcome to the first session of ICFP 2026. I'm Steve Zdansberg from the University of Pennsylvania. Before we jump into the technical content, I want to make a brief announcement about SIGPlan Cares, which is an organization that's there to encourage a welcoming and harassment-free environment at the SIGPlan conferences like ICFP. They're basically a welcoming, friendly ear that you can reach out to if you have any concerns that you would like to discuss confidentially. So feel free to reach out to any of them. You can find all of the contact information on the SIGPlan Cares website, and I think I'm the only member who's going to be here physically this week. So feel free to catch me in the hall or at any of the events if you would like to chat about anything, or you can reach out to any of these amazing folks that you see on the screen. And with that, I would like to jump into this session, which features the distinguished papers from ICFP. These were 4 papers selected from among 10 that were nominated by the PC for their novelty, depth, interest, and clarity. And they were vetted by this selection committee. I wanted to thank them for their work in doing even more reviewing and reading after the conference decisions had been made to select the papers for this session. And with that, our first talk will be a remote speaker, Thibaut Balabonsky, who is going to be telling us about inlining as a space optimization. You can switch to the remote speaker. All right, we can see you.
Okay.
Thibaut, can you share?
My slides?
Yes.
Okay, is that good?
Not yet.
Not yet. No. Just... that way.
It's thinking.
Okay, let me just change something.
That looks better. I think go ahead and take it away.
Sorry?
That was fine. That looks great. Go ahead and start.
Okay, thank you. So good morning, everybody. So I'm sorry I cannot be here in person to present you, but I hope you will enjoy the conference. And I still would like to participate by telling you this story of actually teaching projects that gave some unexpected fruits. So this started with my original goal was to build a new course on computability and complexity, which would not be based on Turing machines, but on programming languages. The idea is that when we have some undergrad students, they might not all be at ease with the math, but they are all familiar with programming. So I want to use as a computational model a simple functional language and with a clean semantics and provide very rigorous proofs of basic computability and complexity results. And one thing that quite soon emerged from this is the question of how we can characterize complexity in a way that is really dependent only on the language and not on the implementation. So let me say a few words about what we expect from such model of computations. Computability, that's the question of characterizing problems that can or cannot be solved by an algorithm. There have been many models historically, Turing machine, lambda calculus, many others later. And the interesting property we have here is that they all provide the same answer. They all characterize the same set of computable problems. So computability is something which is quite of universal, which is a very robust notion. The complexity, it's a refinement of this question. Now the question is, how can we characterize problems that can be solved by an algorithm under some given resource constraint, for instance, resource of times or constraints of memory space. Here the situation is not as clear, but it has been observed that there is a large set of machines, which are called reasonable machines, which include Turing machines, and which can simulate each other with a polynomial time overhead and a constant factor space overhead. So this is called an invariance result, which is really important because it ensures that all these models, all these reasonable machines, define the same notion of p-time or of log space, for instance. So complexity is also robust, provided we can fit into this invariance result. So what is the situation of the model we know the most of? Turing machine, we can measure time by the number of transitions and space by the length of the tape. This is reasonable, more or less by definition. And then we could, for instance, take a look at RAM machines. We have the number of transitions, which is still a reasonable notion of times. And for space, it's a bit different. If I just count as space the number of used memory cells, then that's not enough. But if I also take into account the actual size of the data that are represented, that it becomes reasonable. Now, what is the status of the lambda calculus here? We would have a natural candidate for measuring time, which is just the number of beta reduction steps. We would also have a natural candidate for measuring space, which would be the size of the terms. This is sometimes called ink space in reference to the quantity of ink that I need to just write down the terms. Is this reasonable? That's not clear because beta reduction, that's a complex operation. It's based on a meta-level substitution, it explores some subterms, it duplicates some other subterms, it does a lot of things. So it's not immediately clear that taking this as an actual computation unit is appropriate. Still, there have been a few positive results here. Starting in the mid-90s. So we have had implementations of lambda calculus in Turing machines, different implementation, one based on term, which allowed to prove that the lambda calculus is an invariant model for space. Another, which is more based on an abstract machine, which shows that the lambda calculus is invariant for time. This has also been extended more lately. We also have the other direction of the simulation. That means a simulation of Turing machine in the lambda calculus using only well-behaved terms that preserves time and space complexity of Turing machines. So all this is good. The only thing which is a bit troubling here is that we have implementation which is invariant for space, implementation which is invariant for time. Until very recently, we didn't have any implementations of lambda calculus that were invariant for both time and space simultaneously. And even these solutions by Forster, Kunz, and Roth, and this just a few years ago, it's not entirely satisfactory because it's actually based on two distinct machines, one which is appropriate for space, one which is appropriate for time, running them in parallel or in alternation, and then just monitoring them to stop the one of the machine whenever something is going wrong. So this is a trick that technically solves the problems, but does not explain much about what is going on here, of how we can reconcile time and space. So that's my goal here. That's providing a simple implementation of the lambda calculus in Turing machines that will be both time and space invariant at the same time. So let me give a few more words on the space-time dilemma of the lambda calculus to see what all this is about. The most naive implementation of the lambda calculus we could imagine on a Turing machine would just be to write down the terms on the Turing tape. So this is actually good as far as memory is concerned, because the length of tape I am using is precisely ink space, that is the measure of space based on the size of the terms. The problem is a problem of size explosion. That is, I can have very short reduction sequences that produce huge terms. So here's a simple example. I have I, which is the identity, delta, which is a function that duplicates its first argument, And if I evaluate this, I will first duplicate the identity, which is not a problem, then duplicate a slightly larger term, which is still okay, and then duplicate larger and larger terms until this does not even fit on my page anymore. And this is obviously a problem, and actually not a problem for space, because as I've said, this takes a lot of space, but that's still the space that is predicted by the model, so that's okay. But this is a problem for time, because for writing this big term on my tape, I actually need an exponential time. So there is a well-known solution to this, is to switch to shared implementation when I'm using pointers to share some subterms. And this is also actually in some way what is happening in any actual implementations of lambda calculus in an abstract machine, for instance. So here the subterms will be managed by pointers or closure containing pointers. And so for instance, instead of duplicating my argument I will just have 2 pointers to it, and then again and again. And these pointers allow me to have a shared representation of my terms, which avoids this problem of explosion. So which is first one good thing, and it has another very interesting property, which is called a subterm property. That means that every term we use here are only subterms of my original term, which means that this can be compiled. I can represent all the terms I'm using only by pointers to the original term, which is quite efficient. So this is a key property for ensuring that my implementation is invariant for time. So problem solved? Well, not quite, because I've just created a new problem of space. The pointers cost something. Not much, but still something. When I have several pointers, I will need logarithmic space to represent each of them, and so I will have to pay a logarithmic space overhead for pointers, which in some case will be worse than the problem we had at the beginning. So this is another problem called pointer explosion, which is symmetric to the term size explosion. So finally, I have a natural way of measuring time, which is the number of beta steps. I have a natural way of measuring space, which is the size of the terms. Each one seen alone is invariant, but they seem to be incompatible. And so that's really my question here. Is it possible to have them both invariant together? And so this is my contribution. This is my what I want to present today. That's an invariant implementation of the lambda calculus that is good for both time and space. The idea is really, really simple. That's based on the graph implementation, in which we just use pointer only for terms that are costly enough. So that's mostly graphs, and I will just perform inline substitution of any term that is too small. Too small, that means smaller than a pointer. Whenever one of the terms that I would like to put in my heap is cost actually less than the pointer that is required to point this address in the heap, then I will just inline my term. So here's an example of what this could give. First, I have to duplicate the identity, which is a very small term, so no problem, I can inline it. Then I have a term which is slightly larger, so I can put it in the heap, and again a few times. But after a few steps, I have more entry used in the heap. If I want to have additional addresses, I will need larger pointers. So maybe at some point, my term here will actually cost less than a new pointer, so I can again inline it. But then I have an argument which is bigger than the one that we had before. So here definitely it is worth an additional pointer. And I can go on this way. So formally, this graph of terms machine will be defined with configuration containing both a term and a heap, where each term may contain addresses from the heap, both in the term part and in the heap part, which I just have a requirement that all this is acyclic. And I will have 2 variants of beta reduction, space-aware beta reductions. That means whenever a lambda abstraction, lambda xt, is applied to some argument u, then I will first consider the first available address in the heap, consider the size of this address, and then compare it to the actual size of the terms of my argument. And then, depending on which one is the lowest, I will either allocate a new heap entry with my argument or just inline the argument. I also have two additional rules for managing the heap. When I have my evaluation context is focusing on an address, then I can just look up the corresponding term in the heap, and also a garbage collection rule, which is applied eagerly to remove parts of the heap that are not used anymore. So my claim is that this very simple machine is actually time and space invariant. The space invariance is the easy part. It's just because with my space-aware beta reduction, configurations never cost more than the terms they represent, up to some constant factor. The hard part is proving time invariant. Actually, that's at least half of the paper is about this. Because I do not have anymore the subterm property, which means that here I create terms which are not directly some terms of my initial configuration, which means that I will have to bound the size of these new terms. I will have to find new invariants to bound this, and also to bound the number of substitutions steps that I have between two beta reduction steps. So you just say a few words about the first of these two questions. So if I'm starting with the initial configuration of a term T0 with some empty heap, I'm performing some number of reduction steps, here n reduction steps, and I take any element in the heap, then its size is actually bounded by the size of the initial term and the length of the reduction sequence. Why is that? It's a combination of two ingredients. The first one is that I have in the heap only original subterms, that means subterm of T0, modulo some substitutions. This is a quite subtle property. It is not true for any evaluation strategy, but it holds for both call by name and call by value for two totally different reasons. And the other ingredient is that these substitutions that are applied to my terms are only substitution of small things, either pointers or small terms, that mean terms that are smaller than a pointer, which explain this logarithmic term depending on the number of reduction steps. And the consequence of this is that my copy operations are this time guaranteed to be reasonable for time. And so finally, what we have here, we have proved that the natural time and space cost model for the weak lambda calculus are actually not only reasonable, but even compatible one with the other, despite the apparent tension between them. And the consequence of that is that the weak lambda calculus, or usual functional programming language, is actually an appropriate vessel for characterizing the most prominent complexity classes like log space, p-time, p-space, etc. And the main idea of this is just heap-based implementation, which is something which already existed, greedy application of garbage collection, which is also already existing. Maybe the only new thing in this here is inline substitution of the term which are too small. Well, now all this development is really related to weak reduction, that is not reducing inside lambda calculus, inside the lambda abstraction. That's an appropriate model for functional programming languages. One question would be to extend this to strong reduction, but it's relying on the weak property on many parts of the proof, so I really have no idea how we could deal with this. Well, I thank you. If you have a few questions, I will be happy to discuss.
Thank you. If you have any questions, please step to the mics in the hall. And can I ask the next speaker to start?
I have a question about the reasonableness of time. It's based on the sub-expressions being in your original program. Does that mean the asymptotic complexity depends on the size of the original program? If your original starting code is 10 times as big, is it 10 times as long for evaluation?
Yeah, it gives it might actually give a bound. Yeah, the size of the terms which I will have to copy will actually depend on the size of the initial term. Yes.
Okay, thank you.
And which is expected because the complexity is always asymptotic with respect to the input of the program. So that's something which is to be expected.
Okay, thanks.
Thank you.
Been removed. So why is it not? Why is it blocking the silence? There should be a. Oh. Okay. Where's mute? Bottom one here. Right. Built-in screen. Nope. Is presenting from?
Yeah, maybe I can do it like this.
Okay.
All right. Our next paper is about first-class constraint types, and Chung-Kit Lam will be speaking.
Hello, good morning, everyone. I'm Chung-Kit Lam from HAUST, and in this talk, I'll be presenting first-class constraint types. This is a joint work with Florian Ferrari from ENS de Lyon and Lionel Perot from HAUST. So first, a bit of background. In ML-style polymorphic type schemes, the type system is stratified. So we have simple types, which can be type variables, simple functions, booleans, etc. And on the right, we have the type schemes, which can be for all quantified over these simple types. It is stratified because you cannot use type schemes inside the simple types. And one common generalization of this is to add constraints for the instantiations, and we get constraint types. So instead of allowing arbitrary instantiation, we only allow instantiation that satisfies certain constraints, for example, subtyping and type class. However, at the end of the day, this is still type schemes, so this is still stratified. If we want to get rid of the stratification, we can go first-class polymorphism. And this gets us first-class, we get this system F. So in this case, we are no longer stratified, so we can pass a polymorphic function inside the function, for example, and apply it truly polymorphically. So we can apply it to, for example, an integer and a Boolean. And if we apply similar principles to constraint types, we get first-class constraint types, which is the contents of this paper. Here, we can use polymorphic types and also constraint types as first class inside this type system. And in this paper, we focus on subtyping constraints. So here's the agenda for this talk. So first, I'll talk about the syntax and declarative typing rules for FCCT, the first-class constraint types. And then I'll talk about the properties of FCCT and roughly how we prove them. And then I'll talk about the type inference semi-algorithm, which is sound and complete for this. And this is also a vehicle for proving the properties of FCCT. And at the end, I'll touch on the future work. So first, here is the syntax for FCCT. As you can see, the term level syntax is very simple, unlike system F. So this is basically untyped lambda calculus, but with some base type. So so if your terms are wrong, they actually get stuck instead of evaluating if you just have functions. For types, this is the first-class constraint types as promised. And we do call by name reduction here. So we only reduce outermost, leftmost. Here are the typing rules. They are mostly standard. In particular, we have T-subs, which allows you to upcast the type of a term, provided that you can prove the typing, subtyping relation to hold under the context. And we also have T-constraint, which allows you to assume a certain constraint to be in the context, type the term, and then type the term in the original context as a constraint type. In order to use the T-subs and T-constraint rules, we need subtyping relations. So here are the subtyping rules. There are quite a lot of them, but they're mostly for manipulating structurally in the type. In particular, we focus on S-height, which is in the upper left, which is about you can get a constraint from the context, so which is assumed by the T-constraint rule, and say that it holds under the current context. And then for the bottom right, we have S constraint L rule, which says that you can upcast a constraint type into the unconstrained form, provided that you can prove the constraint to hold under the current context. And this is very important for soundness, as we will see in the next slide. So a problem with this system is that we never really talk about inconsistent constraints in the context. So if we assume some inconsistent constraint, for example, we say that a Boolean is a subtype of a Boolean function, then we can type true first as a Boolean and then upcast it to a Boolean function. This also means that under the same context, we can type true applied to false as a Boolean, because we first type true as a Boolean function and apply it with a Boolean. And this also means that we can type the same term under the empty context as a constraint type. So this may be something that we want to avoid if we don't want our terms to get stuck. But actually, under the call by name evaluation, this is fine if the term never really gets evaluated. So if this is only passed into a function that discards the parameter, then it is fine. So ultimately, what we want is we want to prevent these terms from propagating to the uppermost level. So we have this T top level rule, which states that if you want to type a term, which is top level, not a subterm, then you have to show that it has a weak hat type, so you cannot have outermost for all quantification or outermost constraints. And the previous subtyping rules, in particular the S constraint L, says that the only way to do this, to get rid of the constraint that you may introduce previously, is to show that it holds under the current empty context. So this actually gives you the soundness. So here are the properties of the FCCT declarative type system. So first, we can prove soundness via standard progress and preservation. And we show that all FCCT terms must terminate under call by name reduction. And this is via elaborating the typing derivation into something we call system FFFF, or system rainbow, because there are different colors. And also, we show that all call by name terminating terms are typable with FCCT. This is via a sound and complete type inference semi-algorithm. And the last two properties together shows that FCCT characterizes call by name termination. So about the system rainbow, it is actually the variant of system F. So we added other colors to the arrows to encode constraints and subtype coercion in the system. And we have rules that can elaborate typing derivation in system FCCT into system rainbow, as shown. Yes, sorry about the size, but the idea here is if FCCT term reduces in one step, then in the system rainbow, it should reduce in at least one step. And because system rainbow is a variant of system F, you cannot really get infinite reduction. So it tells you FCCT terms cannot reduce indefinitely. And now let's move to the type inference with the semi-algorithm, which we call FCCT-I. So first, let's look at an example for typing a function. So we first type the body of a function as tau, given that x binds to alpha. And we also get some constraint, which is shown on the right. From that, we can type the whole function as for all alpha to a constraint type corresponding to the body. And this function type doesn't emit any constraint. Now, if we look at typing an application, here we need to split it into two passes. So we first do constraint generation, and then we solve the constraints. So we first type the two individual subterms of this application. They are standard. and then for the application result, we just say that the type is beta, and we have a constraint for beta. On the left-hand side, it is the actual the type of the function that we are applying. In this case, it is a known type, but in some cases, for example, if you are using a variable, for example, it may just be a type variable. And on the right, this is the expected function signature. So bool corresponds to the parameter we pass into the function, which is true in this case, and beta is the expected return type. So we get this constraint and say that the return type is just beta. And the constraint generation is purely syntax directed. So this is very, so we don't really have any non-terminating issue with constraint generation. Now we have to solve the constraint to know what beta can actually be. So this is actually a bottom-up approach. So we, given a conclusion, we try to find out what bounds should be placed for beta and alpha in order to get the desired conclusion. The first thing we can do is to get rid of the left for all quantification. And we can do this via the S4L rule and apply the transitivity rule. So what we have to solve is the thing on the right-hand side. And then we can apply the S-fun rule, which splits the complicated constraint into two simpler constraints. And in this case, we can just read from it that alpha 1 should be a supertype of bool, and also beta should be a supertype of bool as well. So this gives us the desired result. And actually, in this system, we can do term readback from the constraint types. So for lambda terms, as for function types, we can read back a lambda term. And for constraint type, we can read back a let expression, where each subtype constraint is translated into a let binding. And in particular, if we look at the function subtyping relation, so the second last row, it is the original function application. So this translates to a let binding, where the value is a function application result. And if we have applied the S-fun rule, which splits the function subtyping constraint into two smaller constraints, we can see that this actually corresponds to applying the function. So here, x alpha is bound to the parameter passed into the original function, and x beta is bind to the body of the function. And note that x alpha is defined before, so we get proper nesting in this system. Here are the properties of the semi-algorithm. So it is sound with respect to the declarative type system. And the lower bounds correspond to variable bindings, as we see in the last slide. And in the paper, we show that constraint solving actually corresponds to call by name reduction. In particular, S-fun corresponds to applying the function, and S-constraint corresponds to the outermost leftmost reduction. From this argument, we can show that the semi-algorithm terminates for terminating terms. And this also gives us the proof for FCCT being able to type all call by name terminating terms. In the interest of time, I will not get into the details of the FCCT I+, which is the plus version of the type inference semi-algorithm. So this one actually terminates, but it is no longer complete with respect to our declarative type system. So the idea here is the non-termination problem in our semi-algorithm is due to infinite type variable instantiation. So remember, at first, in the function application example, I said we can get rid of the outermost for quantification by substituting it with something. That part is actually causing all the trouble in the non-termination part. And we can finitize that by bounding and merging these instantiation. In the actual system, we actually mark this instantiation with marks, and then we can have we can only finitize it by bounding the number of occurrences of those marks. Because we are now merging instantiations, this also means that we can have multiple lower bounds for the same type variable when we are doing the constraint solving, which is fine because we find that this actually corresponds to a form of non-deterministic value binding. So for example, if alpha has two lower bounds, tau 0 and tau 1, this kind of corresponds to two possible bindings for x alpha. And in the reduction semantics that we are considering, the system can choose whatever way to bind it. And for every single location that you are substituting, it can choose whatever. So it is not choosing one and substitutes for all position. So you can have different results for each position. And the soundness argument for this is that it cannot go wrong under any possible reduction. And at last, for the future work, we want to support call by value evaluation because currently we only do call by name.
And then we also want to see optimized by partial constraint solving. Because currently in the constraint generation part, we are accumulating all the constraints without actually solving them. And as you can see in the term read back, we can map the type back to a term. So this means that we have all the information in the type reduction. So if we can do partial constraint solving, this may make the system a bit more scalable. And also, we want to look at soundness by elaboration. Because currently, the soundness is provided by a separate progress and preservation proof, and instead of the elaboration. And at last, we are looking into mechanization. And in fact, one of our group mates is already doing a lean formalization of the declarative system. That's all for me for today. Thank you.
Questions? Questions, come to the mics. While we're waiting for some, I'm wondering, you mentioned that it doesn't yet work for call by value. I'm wondering if you can shed some intuition about what's hard or obstacle about that.
Yeah, basically, let me go to, yeah, basically, we rely on this argument saying that so we only defer the instantiation of the content of the function until it kind of reaches the top level. So this only works for call by name. So if we need to do call by value, we have to change the constraint generator a bit.
Great. Question.
Hi, great talk. It's very natural generalization, very elegant, but I was just curious if there's treating constraints in this first-class way buys you any additional power? Like, are any programs that I would have wanted to be able to write in something where constraints are not first-class that I can now?
Actually, we have some examples in the paper, but due to time limit, I didn't add it to the slides. Gotcha. So yeah, we can chat.
Hey, so I noticed one of the subtyping constraints you had was instantiation, and I think there's old paper on STLC with a very expressive sort of intersection types, and it had the same property that well-typed terms were precisely the terminating ones. Have you looked at that connection?
Yeah, we actually look at intersection types. So yes, they do have similar characterization, but we think that our type inference approach is much simpler than the intersection type-based ones.
The type inference approach. Thank you.
Just one more.
Interesting work. I noticed one thing along here was that you were actually separating the notion of constraint from the notion of quantification, which I hadn't seen before in a system like this. I was curious if that also gave you some additional expressive power, that is, whether there are things you can write with those separated constraint types that you couldn't write when they're merged with quantification.
Yeah, in the declarative system, we actually allow non-local constraints. So you can bound variables that are not local to the quantification. But in the inference, we are actually only local.
All right, let's thank our speaker one more time. And Leo Lampropoulos will be giving the talk. Great.
Great. Hi, I'm Leo, and I'm going to talk to you about work that we did at UMD together with my co-authors. This work was led by Alp, who is my recently graduated PhD student who could not be here due to travel and visa conflicts. So this talk, as you could have guessed from the title or from the fact that I and Harry are both in it, is about property-based testing. And when we talk about property-based testing, we focus on properties. So here's an example of a property. Here's an executable predicate. It quantifies over expressions and returns a Boolean. This particular one checks that if you give me an expression, if I evaluate it with and without optimizations, I get back the same result. Standard optimization correctness. Now, if you want to test this property, you need a few more things, a few more annotations from your system. Usually that amounts to a bunch of things like a generator, a way to print it. So let's see how it all fits together. We start with a checker, the predicate that we care about, and we need a way of generating inputs. So we have a generator that produces some expressions, we check it, and we try again and again and again until hopefully, or not hopefully, depending on whose side you're on, you get back a bug. You get back an expression that reveals a counterexample. Great. Now usually those bugs have a lot of random noise in them, so you need to minimize them. And that's done through a process called shrinking. So you shrink your input. It's a very similar loop. You try smaller and smaller counterexamples until eventually you get back to some minimal or locally minimal counterexample. And then you present that to the user. And that's really property-based testing in the style of quick check that was presented like 25 years ago in this very conference in a nutshell. So what do we need? What are the components? We have a checker, a generator, a shrinker, a printer, and the system that runs the whole thing. Now, a lot of work has been done in automating these things. Some of these things have to be written by users, like the properties. Some of the things are provided by the frameworks, like the way you run things. But generators and printers and shrinkers are all like, users can write them, frameworks can derive them. There's a lot of work there. Now, if you look at this picture, you might be thinking that this is a talk about me wanting to automate checkers away, but no. The talk is about giving users the ability to write their own runners. Why would you want to do that? Well, let's take a look at a couple of runners. So this is the quick check runner that I already showed you. Generation loop, shrinking loop, pretty simple. But a while ago, the fuzzing community came up with a very clever idea to make this a bit more automatic, to get more efficiency or effectiveness from your tests. The main idea is to instrument your checker. So when you run your property, you keep track of which branches you took along the way. And then, instead of starting every generation from scratch, you remember every input that led you down a new path. And once you do that, instead of generating from scratch, you can mutate it. You can mutate your inputs, and hopefully that leads you down newer and newer paths as you keep increasing your coverage of your program. So this is the runner from a tool called FuzzJig that we had built a while ago. And if you put these side by side, they look fairly close to each other, right? So we have the identical shrinking loops, and you would hope that their implementations are very close together. Well, that could not be further from the truth. And the problem is that, in our opinion, the problem comes from the fact that properties are shallow embedded. So let me get into properties first before I tell you our solution to this problem. So what do you need to discuss properties? For the purposes of this talk, I'm going to keep it as high level as possible. So we have a for all that quantifies over things. For all expressions, something happens. Check, which is the something happens. And then a way of running it. So how does quick check work? The way quick check works is pretty ingenious. Like every time I try to explain it or think about it, it's amazing. You have generators be functions from random seeds to some element A, and your properties are just generators for results. So you're sampling a run of your property and checking if it holds or not. It's okay or it fails. So using this embedding, how do we write for all? How do we write run? It actually fits on a single slide, and that's one of the really cool things about it. Here's for all. You give a generator, you have a function from an A to a property, and the only thing you do is you run the generator, you feed it some random input, you get back an A, you run the rest of your property, done. Well, how do you run one of these properties that are constructed using for all? Again, simple, just create a random seed and loop a bunch of times. Either you find a bug, in which case you report it, or you don't find a bug, in which case you keep trying until you hit some limit. Now, I am eliding a few details, and I already see John squinting. Like, yeah, I'm doing bad things with seeds, I'm reusing them, so the actual thing does something weird called splitting. But that's not important. Like, this actually does sort of fit in one line. It captures the core. There is another thing I'm hiding, is that the original loop that I showed you had a shrinking component, right? How does that fit into this picture? Well, now is where the annoying things sort of start, because, well, to incorporate shrinking in this model, I have to change the type of my properties, and my properties are not now generators for results, they're generators for rows, trees of results, because I'm incorporating an infinite tree of shrinks as the result of my properties. I have to encode the way properties are run into their type. And then if you want to play with that and like add useful combinators for it, you do some crazy things that I don't have enough time to explain, I don't want to explain, you don't want to be explained. Like, this is crazy, but it works, and it's amazing that it works. But then a couple of years ago, like a decade ago, we tried to incorporate fuzzing into this, and yeah, my reaction looked a bit something like that, because incorporating fuzzing into this means you have to decide when you mutate, which inputs you're going to mutate, and all of that has to be embedded into this same sort of Jan Rose tree shallow embedding. And the problems we are facing stem from exactly that. It stems from the fact that the only thing you can do with a property that's encoded as a function is run it. I cannot pattern match on it, I cannot inspect it, I cannot give different interpretations for it. So what do we do as ICFP folk whenever we see a shallow embedding? Well, let's make it deep. Okay, but if I had the deep embedding for properties, that would mean I can't use Haskell to write my properties, my predicates. I can't use it to write my generators. I have to write everything in this DSL. So we already have a hard enough time convincing people to write properties, so this is a non-starter. But there are things in the middle, right? We can use a deeper embedding. So what is the canonical one? Higher order abstract syntax, right? This is a very good example of something sort of in between, where the for all and check, which was shallowly embedded before, they were just Haskell functions, now they become constructors in an inductive type. Here's properties, for all and check have the same types, but now if you give me a property, I can pattern match on it. Great. Except there's one small caveat that at some point, if I'm doing some loops over properties, I will need to be able to access the recursive thing in there. What is the element that I'm going to pass in that P? The only thing I can do is randomly generate it, and at that point I'm back into the whole, well, I'm stuck under a generation, what am I doing? So here's the crazy idea behind this paper, and we call it deferred binding abstract syntax. So instead of binding a variable at the use site, we're going to defer that, and we're going to bind all the variables at once at the end. Now, if you think about it even for a second, for any other sort of DSL expression language, this is completely insane. You have one binding site and many use sites. Why would you ever want this? But in a property language, you have for all, check. So you basically have one use site or maybe some dependencies, and you can sort of get away with this, and we got away with this. So here's the actual way this works. Our types are a bit more convoluted now because we have to make weird things to make it type safe. So our properties are indexed by a list of types, the things that it expects, and all for all does is it tags that environment list with an extra type. So we have a new for all. Well, whenever you're going to use it, you're going to have to bind one more thing. And whenever you check, you just bind all of them as a tuple, and that semantic bar there is just a tuple corresponding to whatever heterogeneous list you wanted. Great, so now we can write the same run function that I showed you before. Here's a property. This is rock code, because that's where we wrote it. And you pattern match on it. You have for all, you have check. Well, if you want to check it, all you need to do is call the property by binding the entire environment right there. Types magically work out. And then if you have a for all, you just generate something, run it, keep going. Now, this corresponds to the generator and checking loop that I showed you before. And I'm lying a slight bit, because if you actually want to do it in Rock, you have to follow the convoy pattern, and that's not my fault, that's dependent pattern matching. So yeah, in another language, this might look better, but you can write this. And more crucially, you only need to write these components once. So I can write things like the check function that captures whether a property holds. I can give different interpretations of properties with different features, generation, shrinking, whatever, and those are the ones that deal with the convoy pattern and everything there. And then I can play with those as building blocks. And I can play with those as building blocks and construct, for example, the generation and testing loop, and this is straightforward, simple programming. Like at this point, I don't care about anything dependently typed, which is great. So how well does it work? Let's talk about the good, the bad, and the ugly. The good is programmability. We get a lot of expressive power. The bad whenever you're talking about these embeddings is usually performance, actually not so much in this case, and the ugly is ergonomics. How well does it work, and types, do they get in the way? Well, let's talk about programmable loops. So the thing we did was we went through the literature of the last 10, 15 years. We found a whole bunch of frameworks that were implementing different loops, and all of them, except I think one, were basically leading to an entirely new framework being developed. You needed to go under the hood, take some things out, put some things in, and re-engineer a whole framework in order to make it work. All of these are built in userland. So we start with a generation loop that I showed you earlier. We have the fuzzing loop that was part of FuzzJig a while back. But a line of work came out of that where instead of having feedback be coverage, you can leave that programmable up to the user. That is called targeted property-based testing. So you can have a feedback function that captures other aspects of your inputs. So for example, how long did my program run because I wanted to get into an interesting state? And then you try to maximize that. That all fits within the same framework pretty easily. You can also not do with runtime feedback. You can do something called combinatorial coverage, where you generate a whole bunch of things and then pick the one that maximizes some kind of interaction. That could be useful if your runtime for your properties is really slow. Again, easy to implement on top. You can do crazy things. You can parallelize the whole thing while making sure that you increase the size properly as you go along. You can do integrated shrinking, where instead of using external shrinkers, you use the generators themselves to generate smaller and smaller properties. You can do crazy things. And again, the paper has a lot more details about how you can do that, but the key thing is that you can program all of these things in userland, right? I don't have to go under the hood and implement anything new. I just have these high-level components that are really, really useful in building blocks, and I put them together, and I can experiment fast. And that's really the other thing that is really good, is that it allows for a kind of rapid experimentation that PhD me only longed for so much, literally, because when we built FuzzJig, we had to make a bunch of design decisions, right? And the main design decisions is how do you implement that seed pool? And that has a lot of very impactful decisions under the hood. From how do you store seeds? Do you put them in a heap, a queue, a list? What do you do? How do you pick the next seed to mutate? That is called the search strategy in the literature. How do you pick long do you mutate it for? That's a power schedule. Every single one of these decisions has like multiple software engineering papers associated with it. And what did we do back then? Well, we just copied AFL's choices because to keep the comparison fair, partly because I had no idea how to even go about trying all of these things. But now I have a very easy and rapid way of doing it, which is just try them all. I can just program a very, very compositional thing that allows me to give different interpretations. So we did that as part of the evaluation for the paper. We used Etna, which is a property-based testing evaluation framework. It has a bunch of workloads, a bunch of programs that have already been preceded with faults. And your goal to evaluate generators is how quickly can you find those. It has a very nice visualization that we call bucket charts. So this one shows that 14 bugs were found in under 0.1 seconds and 4 were unsolved. So the bolder the shade, the better your generator. And then we just run a whole bunch of these. And the point here is not which one is best, even though there is one, and now that is now the default for FuzzJig moving forward. The point is that this kind of picture is even possible because we were able to program a whole bunch of these different interpretations of our properties very quickly. Now, the paper also has a lot more experiments in terms of things we were able to do, but in the interest of time, I will not get into them. A few things about performance. The top one is standard quick check implementation, shallow embedding. The bottom one is DBAS. There's not much difference. Sometimes it's better, sometimes it's worse. It actually doesn't have any performance implication as far as we could tell, like meaningful one. But the ugly part, the not great part is ergonomics. So here is what the property from the introduction would look like if we stuck to what I showed you on the slide, right? Again, I said we have a hard enough time getting people to write properties. This is also a non-starter. But this is sort of a core language. So if you go deep into rock notation hacking, you can get into something much, much more palatable, which, again, not as simple as shallow embeddings, but simple enough. And if you have Justine or any other Racket crazy genius student, you can get very good uses of macros and have something that looks like a perfectly reasonable thing. You just have to work in a dynamic setting. Really, though, the main thing that I could not really make work is you can implement this for Haskell, but the ergonomics are way worse than I could get them in Rock, and I don't even have an idea of how I would begin to do it in a type-safe language without any of the nice intricacies that we have in Haskell. You can do it if you make everything unsafe, but that would be the price you would pay. So with that, I want to thank all my collaborators on this paper and take your questions.
Questions, please use the mic.
Hi, Leo. So there's one thing in particular which I wonder whether you can now do, and that's something that we did in the Erlang version of QuickCheck, but never could in Haskell. That is to save a shrunk test case after a failure, because you very often want to rerun exactly the same test case. You don't want to generate from the same seed, because then you'll be doing the shrinking all over again. Can you do that?
Yes, yes. You can do a lot more things, in particular with shrinking. We have a study on that in the paper a bit. But basically, you can do everything that you want to do in Haskell shrinking that you have to write weird combinations for, like shrink2. You can now basically say, oh, give me a way of executing the property over all of its inputs and shrink things in combination, however you want, independently, as a tuple. And if you want to save them, yeah, you have to do side effectful things to do that, but it shouldn't be a problem. So yeah, you get everything you can think of in a piece of paper, you can now code. If you need more annotations, like adding mutators, you might need to change underlying things, but most of the time it's pretty simple.
Any other questions? No. Let's thank Leo again. Could I ask the last speaker of the session, Victor, to come? All right, our next talk is about catenable, splittable, transient sequence data structure, and Alexander is going to be giving it.
All right, so hello everyone. My name is Alexandre Moine. I'm a postdoc at NYU, but I was once a PhD student working with Arthur and François. And once a PhD student, always one, so I'm presenting their work today. So it's about a catenable, splittable, transient sequence data structure. All right, so sequences are ubiquitous in programming. You often need a sequence that is a data structure when you push and pop at both ends and have split and concat. Usually in functional programming, we use lists to do that, but they are perhaps not that efficient for this API. So the goal here is to develop a structure with decent support for all sequence operations, so push and pop at both ends, but also fast splitting and concatenation. This is essential for string manipulation when, of course, you split and concat a lot, but also for parallel processing, where you want to split the data structure, evaluate in parallel, and compose at the end. But you will also like support for persistence and sharing. In particular, if you use backtracking, you need to do a checkpoint at some point. You might want to do a checkpoint at some point in order to go back to this state, but you don't want to pay the cost of persistent at each single step, and you want fast in-place mutation when possible. So in order to implement this kind of APIs, you have usually two kinds of traditional design decisions. Either you go the ephemeral way, where it's fast because you mutate in-place objects, but the updates are destructive. So creating a checkpoint requires making a deep copy of the data structure, which is linear in the length of the data structure. But then you can go the other way around and try with a fully persistent data structure, which will be very slow because it implicitly creates a checkpoint at every single operation. So today I'm going to present a transient data structure, which is kind of in between. It has an ephemeral API, a persistent API, and near constant time conversions between the two. That's an idea that comes from Clojure, and that we argue here should be explored further. So the contribution is sec, a transient sequence. It features sequence operations, so fast push and pop at two ends, get, set, split, and concat, and fast conversions between the two, API, the persistent API, and the ephemeral API. It also comes with an ephemeral iterator, if you are going to mutate the data structure, and compact memory layout. In this talk, I'm not going to present the whole data structure, but rather to focus on a simplification and do a warm-up with transient arrays, recall the benefits of using k-way trees, and then explaining how we are going to optimize this implementation using ownership ideas, and then scale the approach to the full data structure. All right, so a warm-up with transient arrays, sorry. So we have two modules, ephemeral and persistent. They implement an array interface, so they both have a type T, this is in OCaml. They have a create function that is the same, that takes the length, a default element, and return the array, a gate function that returns the element at some index, and a set operation that differs between the ephemeral and the persistent API. In the ephemeral case, you're going to mutate in place, so you return the unit value, whereas in the persistent case, you return the new version of the array. And then you have two conversion functions, a snapshot that converts an ephemeral array to a persistent one, and edit that convert a persistent array to an ephemeral one. How to implement this API? Well, as I said, you have two rather standard choices. Either you go the full ephemeral way, so you use raw OCaml arrays that have, of course, constant time access, a very compact memory layout, but you need to pay linear time for copying for the persistent API. Or you can go the other way around and use a persistent binary tree to represent your array. Then persistence is for free because you use a persistent tree. But then you need to pay a logarithmic factor for accesses because you need to go down the tree if you store the elements at the leaves, and to pay the price for numerous indirections. A good compromise that we are going to develop here is to use trees, but with large branching factors. So we are going to consider k-way trees, that is, trees where the nodes are represented using a chunk. And a chunk is a fully or partially filled array of capacity k. So using these k-way trees, what are the asymptotics of our transient array? Well, these asymptotics are going to feature the log k of n being the number of elements. And I want to insist here that this log is very small in practice. If I take k equals 16 and n is equal to 4 billion, then the depth, this log k, is equal to 8. So it's really a very small number. And then if we need to do an update, we're going to do a copy on write. So if I'm modifying an array in the tree, I'm copying to preserve the persistent views. So you need to pay a linear time in k. All right, so the asymptotics here are for get a log factor because you need to go down the tree and find your element. And for set, you need to update every single node in this path of this binary tree. So it's k times a log. And then we have a very reasonable space usage. So one annoying thing here is this k factor, in particular when you use the array in an ephemeral way, because if you know that no one is having information about the array you're mutating, you should be able to mutate in place. You have unique ownership of the array you're mutating. So we are going to develop a little optimization here using ownership informations. So the idea here is that every node of the tree carries an ID. And ephemeral trees have also a root ID. Here, the root ID is here, and it's 8, if you can see. And the invariant is that if a node ID matches the root ID, then we have unique ownership. And we can mutate in place the node without copying it. So we can update in place. Otherwise, if we don't have ownership, or if we are in a persistent API where there is no notion of ownership, then we update the nodes using copy on write. So we copy before and then write inside. And this approach has two very good behaviors. The first one is that recently modified cells are uniquely owned. When I'm doing a copy on write, I'm using the root ID of the node ID of the current tree. So every chunk I'm copying, I'm ensuring I have their unique ownership. So if I'm modifying a bunch of chunks on the same part of the tree, I will do copy once and then mutate in place. And then it also means that conversion from persistent to ephemeral is very efficient. I just generate a fresh root ID, and then I'm ensuring that I don't have ownership of any node, so I will preserve all the prior views. So the asymptotics here are the same as before in the worst case, so log for get and k times the log for set. But this time, if we do a set on own cells, we just pay for the price of finding the cell we are modifying, so it's a log. And if we are modifying consecutive cells using an iterator, for example, then you can amortize the cost, and it's constant per cell. Very efficient conversions again, and a very reasonable space usage too. An interesting trade-off here is the choice of k, because if you choose a large k, you will have an even smaller log, so it's very efficient for read operations. But if you have a large k, you will pay a price here in the worst case set. So it depends on the read-write ratio. All right, so enough of arrays, now jumping to sequences. And we are going to reuse these kind of ideas with a scary picture. So the idea here is inspired by Akar Shagero and Rene and Hins Patterson. So we are designing a sequence. So we need fast access to the front and fast access to the back. So a sequence here, the entry point is here, is a triple of an array with the front elements, an array of the back elements, and in the middle, a sequence of elements, which are the elements in the middle. But the idea here is that we are going to use kind of a polymorphic recursion approach, in the sense that at level 2, here, the front is itself an array of arrays, and the back is itself an array of arrays, and the middle will be, again, an array of arrays of elements, growing each time the factor. So it works. Check the paper for the asymptotic details. And the idea here is that we can also set the arity k independently at each level. So at the root level, you might want a large k to have fast access to the back and front. So we use k equals 128, and then k equals 16 for the deeper depths to kick in this recursive approach. All right, what are the costs? Again, this is the last scary table. We have get and set, again, with the same kind of worst case approach. Here, also get, you might need to pay a k factor because this structure supports split and concat, and because of that, chunks might not be full, and you might need to go to read a chunk before diving into it. Same kind of asymptotics for push and pop, a very efficient split and concat, near polylog, and again, efficient conversions between the two. And a good part of the paper is also about getting rid of this k factor that pollutes and degrade a little bit the asymptotics here. So in particular for get, if we know that the chunks are full, so if no concat was used by the user, then we know that all the chunks are full, so there is no need to pay the price, so it's just a logarithmic access. For set, as we saw, if we uniquely own chunks, there is no need to duplicate them, so it's again just a log factor. And for push, if the update is monotonic, if I'm writing data that is in a not fully full chunk, I can just write my data in the chunk directly rather than creating a new version, so there is no need to pay the k price. Anyway, so a bunch of optimizations. And yeah, I'm reaching the conclusion now. So the idea here is to use transient chunks inside a chunked sequence tree. The optimization, we have a lot of optimization for faster accesses to elements stored in full chunks and good theoretical bounds for transient data structures. You can use these data structures in real life. There are more in the paper, so all the implementation details in OCaml and the cost analysis. optimization for persistent push and pop using views, so again, to avoid duplicating chunks when possible. Optimization for short sequences. You don't need these whole data structures if you have a short sequence, so we can optimize that away. Ephemeral iterators, which are useful because they will amortize the cost of modification. And extensive testing using fuzzing. SEC is available on OPAM as an OCaml package, so please try it out, and the paper too is available. Thank you.
All right, we have time for questions.
Yeah, and I think Francois should be on Discord. Yes.
Yes, I'm here.
Awesome. Thanks for the data structure. This looks really cool. I can basically hear my architecture colleagues yelling at me about cache locality when I tell them about this. So when you run it, did you see any noticeable effect of that for longer things, or do you have any thoughts on the matter?
No, I don't know how to study cache effects really. So we did some micro benchmarks, and we tried to see how changing the constant K affect performance, but we don't really know which caches cause the effects that we observe. And there are also GC effects. So the GC parameters can influence the performance quite a lot. So it's hard to know exactly what is causing the performance that you observe.
So this seems like a lovely data structure. It goes to a bunch of effort to preserve the nice complexity bounds that you have. Do you see either like in your sense or in actual testing whether the asymptotic bounds have some trade-off with in practice performance compared to a simpler data structure that would not achieve those complexity bounds in the worst case?
It's hard to say. I mean, we work to have good complexity bounds, and we work to have good performance in practice. But I cannot say that there is any visible connection between the two. It's yeah. So I'm sorry, I don't know how to give a good answer to this.
All right, thanks. Any other questions while we have Francois here? If not, thanks again for the talk and the work. While we're setting up for the next speaker, I just wanted to remind you these first, go ahead and, the distinguished papers for ICFP. So let's give all of the authors another round of congratulations for their fine work. All right, the last paper of the session is a JFP first paper, and it's about adapting the MVVM pattern to C++ front ends and Agda-based backends. And Victor Sima will be giving the talk.
Good morning, everyone. My name is Victor Cimma. I come from, well, basically from Budapest, Hungary. And I'm going to talk about basically connecting GUIs to Agda-based backends. So first, in the introduction, we are going to visit a nuclear reactor, or at least a very simplified model of it. So here it is. A state of the reactor consists of the number of control rods inserted, as well as the power it is currently supplying. And I also have to provide proofs. And among them, there is one for a threshold that needs to be so the power needs to be below the threshold at all times, otherwise it explodes and we all die. So I always have to provide this proof. And I can't forget it, because otherwise it would not compile. So it's quite useful. And with the help of the Agda2Ajas code extraction tool, we can omit these proofs and get to this tidy Haskell code. Well, again, it's useful, but these have already existed. So what's new then? Well, what is what if the engineers asked us to create a GUI for this? So while I'm using the latest version of C++ GUI, so C++ Qt, so it's something newer than this. Well, the idea actually comes from the .NET world. So the model is responsible. So we break the entire thing into three parts. The model is responsible for business logic. The view model contains all the variables and methods that the GUI needs without actually depending on GUI libraries. And the view is the actual GUI. So we are going to do this, but with our favorite languages. So the model is going to be written in Agda and Haskell, and the other two parts in C++. So basically, what we have to work on is this connection, as well as the connection between Agda and Haskell. So the idea is pretty simple, but there are quite many problems we are going to face. So that's what the rest of the paper is about. But first, I would like to take you on a detailed walkthrough of how this looks like in practice. So is there anyone here who is afraid of odd numbers? Ah, there are some. Nice. So let's suppose that we want to create some kind of a counter which we can manipulate with arbitrary numbers, but which is proven to only contain even numbers. So if we try to make it odd, it breaks and returns an error message, but in a good way. So it doesn't actually explode. So first, in logic.agda, we define the business logic. First, this is just a proof that the sum of two even integers is also even. Just keep in mind that this even integer is a predicate. And also, because this is annotated by at 0, this means that the entire thing is erased, that doesn't appear in the Haskell side. This function takes two integers and proves that they are even, and then returns a sigma type, basically a tuple that contains the result and the proof that this result is even. But the proof part is, again, erased. And finally, we have a function that checks whether both are even. And if both are even, then we can call the previous function, and we can supply these proofs. If not, we return an error message. Now, as the model of the application, we define a new type called appState. This basically contains all the variables that the view model has to access through the lifetime of the application behind IOREFs. So basically, these are going to be mutable because we want to have a single appState object mutated several times instead of creating new and new appState objects all the time and exporting them to C. So hence the IOREFs. Actually, if we want to be really precise, we can even say that we incorporate the proof inside the variable, so it really can only be an even integer. In interaction.agda, we define the functions that can be exported to C. So initialization is just like this. We provide it with a 0 and create a new stable pointer for it. A stable pointer is basically a handle in Haskell, which we can export to C. It's an ID. And then if we put it back to a Haskell callback, the Haskell runtime simply looks it up in a table and provides the Haskell object. So this is how arbitrary Haskell objects can be somehow exported to C. Adding an arbitrary integer to the pointer to the value inside goes by basically defining a function that can be exported to C. So it takes a stable pointer, which can be exported, a C-type integer, and returns a C-type integer. So in C, it's going to look like this. It's going to take stable pointer and integer and returns 1 if it was successful and 0 if it's not, because we gave an odd number. So it's basically a Boolean. And finally, because we have C++, we can incorporate the entire thing into an object, which gets initialized in the initializer, the stable pointer gets freed in the destructor, and then we write some methods. And from then on, it's simple, even to front-end developers who have no experience with functional languages. And finally, who knows Qt? Who has worked with Qt here? Well, then you know it all. It's exactly the same. You don't have to bother about the Haskell part from here on. It's just Qt. And well, this was a rather unrealistic example, but I do have a more realistic one. It's an exact real arithmetic-based calculator. But IORFs and stable pointers and the like actually do not exist in Agda. So we have to direct them to the Haskell built-ins. Actually, we want Agda2A just to generate this code. So with IORF and new IORF imported from the data.iorf library included with Haskell. Well, the easiest way to do this is just putting it verbatim into a foreign pragma, and then Agda2A just simply includes it in the code, and that's it. But don't do it, because from here on, every single use of the initApp function needs to be done in a foreign pragma, and it quickly becomes very ugly. And you can't even use Agda for manipulating this. A bit better is if you also include a postulate with the same type signature, and from then on, you can work with it in Agda and even postulate laws about them if you want to. So for some kind of very complex definitions, this might be the easiest way. But if you want to use new IORF, for example, at many different places, there is a better solution. Because in the latest version of Agda2A, it recognizes the Haskell dot prefix in the name of modules, and if it's like that, then it doesn't actually generate Haskell code for them, but only refers to the data.iorf module of Haskell. And it simply becomes this. It's as easy as if it were written in Haskell. There are other different options which the paper covers, but these are the most important ones. To the best of our knowledge, this is the first paper to enumerate these options and elaborate on their advantages and disadvantages. Now, one of the most exciting contributions follows, and it's a new design for future objects. So why do we need future objects or concurrency at all? Because of this. So if you simply do all the heavy calculation on the GUI thread, then the GUI freezes because it cannot handle the buttons, etc. And also, if it's a very heavy calculation, that the user probably expects a way to interrupt it if he gets bored or whatever. And the problem is that we can't just do it in a C++ std thread and then kill the thread when we get bored, because that destroys the entire Haskell runtime. So we have to have some kind of arrangement on the Haskell side. In Agda, it works the same. Let's stay with Haskell now. The idea is that together with the calculation thread, we also spawn a Haskell thread called a watcher thread. And if we wake it up from C, which we can do, then it kills the calculation thread. And we can do this by using mvars. In Haskell, these are little boxes that can be read and written in a synchronized way. So if we put a unit into this interruption mvar, then it wakes up the watcher thread. The watcher thread kills the calculation thread and writes nothing in the place of the result. If not, then the calculation thread runs and writes the result wrapped into a just. It's quite simple, actually. But futures have existed since time immemorial, and there is even a Haskell library from them from the late 2000s. Well, what this kind of future is good for is that it can be interrupted arbitrarily, and it can also be exported to and manipulated from the C side. So then I'll show you how. in Haskell and in Agda, it just looks like this, a data with 2 MVARs in it. In C, we are going to represent it this way, so there will be 2 stable pointers, one for one MVAR and one for the other, and put into an array. And as we have to pass this array to the Haskell side, we are going to have a type definition for it. So spawning a future means just means expressing the calculation as an IOA and then putting it to fork future, and it returns a future. If you want to export it immediately to C, then we can put a C, and we can give it a C future pointer, so like a pointer to a C array with stable pointers, and the calculation, and it writes the stable pointers there and starts the calculation. And this is how we handle it in C. So we create the array, call this function, which initializes everything and writes the pointers here. And then we wait for the result. This is also a custom Haskell call we create. And we free both pointers. Or to interrupt, we put a unit into the first MVAR. This can be done with a native Haskell FFI call, and it is not actually handmade, and it's much faster than if we made it by hand. And we free the other pointer because we have to free these ones. So it works, but it's not quite simple and convenient, is it? Unless you have C++, because there we have a type that does all these things for us. So basically, we give it a lambda, and from then on it handles everything, and you can just call methods. And it also automatically frees the pointers. As I think that these might be useful outside the scope of this article as well, I have created a package called CFuture on Hackage, if you are interested. Some things about the toolkit called Agdalash, which I have mentioned. So it's basically a Git repo with a skeleton of a project, and also with documentation and basically template files. So just a few words about it, because it's mainly a software engineering project. So entwining Agda and Haskell compilation with C and C++ compilation is done with quite ugly CMake scripts, but you don't have to remake them. So it's done once, and it's nice. So there are 3 projects, one for the backend, one for the front end, and one for the entire thing, so you can compile these separately. There is infrastructure for 3 different methods of testing, in case you don't have proofs yet. And we have template files to put things to, and documentation written in read the docs. And speaking of template files, this is, for example, the place to write quick check test cases to. And it's all about explaining it and making it simple. Just very shortly about the benchmarks included in the article. So why do we have benchmarks? Because many concepts here are not tied to Agda 2Ages, but some are. And if Agda 2Ages is prohibitively slow compared to, for example, OCaml extraction in Rock, so if it generates slow code, then we can't really choose Agda 2Ages in a production environment, and then this entire thing doesn't make sense. But I'm happy to report that it does. So it's actually, so Agda 2Ages generated code actually is at most one order of magnitude slower than Cog-generated code, but actually sometimes it is even faster. So you can choose Agda and Agda 2Ages if you want, and the entire paper makes sense. So to summarize, we have proposed a novel architecture for connecting have functional backends with GUIs. We have enumerated methods for handling Haskell dependencies from Agda code. We have introduced a new future design that is both interruptible anytime and exportable to C. We have condensed all the techniques into a toolkit, and we have proved with benchmarks that this entire thing is practically usable. And most importantly, we have saved the reactor. Thank you so much.
Do we have any questions? While people are thinking of, I have one, I guess. So this seems pretty ambitious to connect C++ to Agda and Haskell all into one kind of project. Do you have any other ambitions about the kinds of applications you'd like to see?
Actually, it would be nice if it could be somehow verified. So if the connection could be verified, because Rock has a similar thing called VeriFFI, and it would be nice to have that in Agda as well.
Any questions? People are anxious for lunch. So I guess let's thank the speaker again, and they can catch you at lunch. I've also been asked to remind the speakers of the afternoon to show up 15 minutes early so you can test out your setups before the talks begin. And otherwise, we'll adjourn to lunch and have a good day.
Thank you.
I should know that. Hello, everybody. So we're still waiting on our session chair, so I'll step in briefly to introduce our next speaker, Gabrielle, talking about tail modulo async await.
Should I start now?
Yes, please.
Can you hear me? Okay, all right, excellent. So hi everyone, I'm going to present async tail modulo async await, which is sort of a combination of two visions, one from the concurrent programming point of view and one from the functional programming point of view. And we will start off with a simple exercise that I could give to my student, which is to implement a file crawler. So a file crawler takes a path, fetches the content of the path, then recursively crawl all the file and the directory under this path, and build a tree of files and directory. And we could have 3 questions or 2.5 questions. First, implement a file crawler that return a tree of directories, and it should also handle symbolic links and follow them. And then, as in the second time, make this crawler concurrent. And finally, we will have a bonus question for very good students, which will be to handle sharing and cycle due to hard links, for instance. All right, so let's start with the first question. And if we have good students, they might implement it like this. We have a data type that describes a tree of directory and path and file implemented as leaf here. And then the implementation is a basic recursive function that first classifies the paths to know if it's a symlink, a directory, or anything else, in green here. If it's a symlink, we can directly follow it and explore it. So we have a recursive call here. We know that this recursive call is a tail call, and so if we have a long chain of symlink, then everything will behave nicely. If we have a directory, we get all the children, and then we recursively crawl all the children. And finally, in any other case, we make a leaf and we stop there. For the recursive call along the children, we have an auxiliary function, which is basically a listbot map, but I've extended it here to show it in more precisely. And in particular, we note that one of the recursive call, probably the second one here, will be tail modulo constructor. And so we get advantage of tail modulo constructor as well. Okay, so that's a nice implementation. It is elegant functional code. There is a nice interplay between the recursive functions. The stack usage of this function is bounded by the depth of the file system tree, which is not terrible, but not great either. But the good thing is that it's not affected by the width of the file system tree, thanks to tail modulo constructor. So we've got at least that for us. It is strictly sequential, so we will try to amend that. And it unfolds a graph. So for example, if I have the file system on the right with a symlink between bin and /user/bin, I will duplicate the whole tree. Okay. So far so good. Now let's start thinking about trees and concurrency. And in particular, the second question, which is to make a concurrent crawler. So if I want to make a concurrent crawler, I will use async await here, which is a classic mechanism for concurrency, in particular in functional programming languages. And so I sprinkled my code with async await. I've made the crawl function asynchronous. Here I have marked with a syntactic annotation, but it's pretty easy to implement otherwise, and used await in all the recursive call. And if you know anything about async await, you know that I've made the code a lot worse by doing that. So first off, there's going to be issue with redirect chain, because here I've broken the nice tail recursive call that I had for symlinks. In addition to that, I have lots of waiting tasks, because for every directory node, I will have a task that waits for all the children. And the worst of all is that this is actually still not concurrent. Because if you look at the last line, the semantic of this would be to crawl H, await this task, crawl T, and then await this task. And so we've actually forced a sequential implementation here. And this is due to the fact that those are two sub-arguments, and we have a fixed execution order for sub-arguments. So our main contribution is that with tail modulo async await, all those problems are fixed. All the recursive call will be tail. There will be no superfluous idle task, and we will obtain a nice concurrent and parallel implementation automatically. So how does that work? To explain that, let's look at the issue with redirect or with symlink chains in more detail. In this particular bit of the code that I have zoomed on here, we have the tail position, which is the bit in red containing the await and the recursive call. And if we do a naive execution of a long chain of symlink, we first crawl a path with a feature associated to it. It is an asynchronous function, it has a feature. Then we launch a subtask which has a feature associated to it. Then we launch a subtask, and so on, with each one having a feature associated to it. Then finally, we obtain a leaf, possibly. We resolve the feature, the last feature to the leaf. Then we await, and we resolve the previous feature. Then we await, review, and so on and so forth. And at some point, we've done all the tasks. We've resolved all the features. And we only have to clean up what's left. In particular, there are lots of tasks to clean up. We can remove all the tasks, and also lots of memory to clean up. So as you can see, this is very wasteful. We're accumulating a long chain of things. We could instead exploit the tail position. And let's look at how it would work here. Instead of, I have my feature here, and I have a promise, which is a hole to fill with the content of the result. And I can record that this path, this call to crawl, will have to fill this feature. And then when I launch a subcall, I will simply launch the subcall, record that it has to fill the same position in memory, and then get rid of the previous task. Mark it as done, and then the GC can remove it and get rid of it. And so on and so forth. We can crawl through the various paths, and eventually we return a leaf and immediately fill the future and finally get rid of the task. And so in this case, we have a nice constant memory usage or constant task usage, I would say, because we get rid of the task as we go. So this is a pretty well-known optimization in the async await literature, which correspond to something called forward. And the insight here is that forward is just an await in tail position. And so we can treat exactly the same and discover it automatically using everything we know about tail position. All right, so that's handle chain of symlinks. But we can, in fact, do more than that if we combine with constructor, and in particular, tail modulo cons. And the idea is that in a concurrent context, we can have several tail calls at the same time. Let's look at an example to see that. Here I have some execution in flight. I have my memory on the left, my task on the right. I have made a first call where I have explored some directory and obtained some children, and I have 2 tasks for each of those subcalls. And I have located where I should write the result of each of these tasks. And for example, I can look at the second one first, and it will discover a directory, for instance. And then I spawn additional task and mark this task as done. And then I can get rid of it. Here I have kept the tasks that are done, but it's only for explanatory purpose. And then I can keep going. For example, this task result in a leaf, and I'm done with it. And this task has more things to explore. And so if you're familiar with tail modulo cons, this is very similar to the destination passing style technique that has been used to implement tail modulo cons, except this time we can have tasks that behave concurrently and we don't have to have only one tail. So there is an interesting question when it comes to this, and in particular, what is the semantic of such multiple recursive call? And so let's do a small semantic interlude to look at this more precisely. In particular, we should be very careful about argument evaluation order when looking at such code. There are 2 interpretations here. A first interpretation is a semantic similar to this code, which be to first await one of the subtasks, first launch one of the subtasks, await it, and then launch the other subtask. And so this corresponds to a sequential semantic. It only allows one tail call because we have first have to await the other. And it's very similar to tail modulo calls. A more interesting semantic might be to launch both subtasks concurrently and then await them before awaited. So this corresponds to a parallel semantic, and it allows several tail calls, but it allows arbitrary interleaving between each of the subcalls. So in the paper, we introduced 2 keywords, async or async par, which allow one or the other. But in fact, in the formalist, we can tag this on a per constructor basis to be very fine-grained about the semantics that we choose between the sequential and the parallel semantics. All right, so we have a nice semantic and a nice programming contract. Let's look at the code transformation a little bit and how this is implemented. And the idea will be to use a transformation that is a little bit like destination passing style, but using what we call a destiny. And the destiny of the computation is the place where the result will be. And the key idea is that a destiny is basically the intersection between a promise and a destination. So a destination is a write once pointer to the place where the value to be computed will be located. And we will use that to fill the result. And on top of that, the destiny is concurrency and termination aware. And so we will be able to know when all the results, all the concurrently filled result will be filled. And so what it looks in practice is, has been presented in the code above. You have both, you have first a fill that creates the cons and put it in the destiny. And then you have forking tail call to each of the subtasks. And we know that both of those are tail. So you can look at the ICFP paper and appendices for more implementation details. And this is a good point to specify that all of what I'm talking about here has been implemented as a syntactic transformation. So it's still a prototype, but it works nicely for such kind of code as a PPX on, for OCaml. All right, so we had answered most of the question and made our proposed code for our question elegant and concurrent. Let's talk about this bonus question, the handling of sharing. And it turns out we won't have much to do, or the student will not have much to do. We can expand our approach to handle sharing almost directly by simply introducing a new construct, this letMemo construct, which will memorize the rest of the computation using the key. And this works very well because now the terminal position in the rest of the code are indeed terminal, which would not be the case normally for memorization. It's pretty hard to preserve tail position when doing memorization. So there are limitations for this. It's still a little bit work in progress. And in particular, we can have only one entry point per function, and memorized code must be tail. If you have a code that is not tail, it cannot be memorized. Otherwise, it handles cycle and everything you can imagine about your graph of tasks. And the key idea behind this is that instead of storing value, we are going to store destiny inside the memorization table, and it allows us to store partially available data. All right, so our contribution is this transformation, tail modulo async await. It allows tail call in asynchronous context. It extends to constructor very well, and it gives a new take on automatic parallelization and allow to write functional tree and even graph walk and get parallel constant stack code almost immediately. I will let you look at what all we have in the paper, and we have a prototype implementation that provide both async await and memorization. Thank you.
Thank you very much. We probably have time for one short question, if anybody wants to come up to the microphones. Okay, thank you very much. Our next talk is going to be a pre-recorded talk. Unfortunately, the speakers are not here for the live Q&A. So keep your questions for them for later. Thank you very much, Gabriel. Okay, so the next talk is set theoretic types for Erlang in practice, and I believe this is Albert giving the talk.
Hold on a moment, Albert. We can't actually hear you on our end.
Welcome everyone, and thank you for the opportunity to be able to talk about this topic. My name is Albert Schimpf from University of Kaiserslautern, and we are here to report our experience on getting set theoretic types to work on Erlang code bases used in practice. A short overview of our project and our goals. Analyzer is a static type checker for Erlang, in Erlang, and built on set theoretic types. It works one top-level function at a time. Function, its spec, and the specs of everything it calls go in. That becomes a constraint set, and the solver solves it. In our case, it's called tallying, basically a generalized unification algorithm over a type algebra with union, intersection, and negation, which returns possibly multiple solutions instead of just one. The result is either OK or a type error, which could be further split into different categories like a non-exhaustive branch or a redundant clause, and so on. The type specifications it trusts come from OTP, Erlang Standard Library, plus our own overlays, which I will come back to that later. So what did we do? The solver core is itself Erlang, so of course we pointed our own checker at it. 29 modules and just close to 800 specifications, and we managed to fully verify the core finally. Plus 5 standard library modules as an outside reference. Here's a quick overview over the type specification language. We have first-class unions in the type alias. We have second-class intersections, so these two arrows separated by the semicolon. That's Erlang's own syntax for overloaded spec. And at the type meta level, we have type difference and therefore negation. Second clause of lookup only ever sees what the first one did not take. So x is an integer, which is implicit in the semantics of the Erlang runtime. Currently, there are 3 active projects which make use of these not enforced type specifications. We have Dialyzer, which infers success typings and reports definite errors only. So basically a static analyzer, not a type checker, and the oldest one of those 3. We have Equalizer from Meta, which is designed to be used for its internal company codebase and does appropriate precision trade-offs. And Atomizer, which tries to keep the whole algebra and turn exhaustion on by default. So we aim for more guarantees and thus pay in analysis time and in false positives. Here is an example from the OTP standard library, filter map. Showcase why we might need the full power of set-theoretic types. It's a function which can both map and filter a list at the same time. The specification is too coarse to be useful sometimes though. First, the predicate as shown may return a plain Boolean. Here. That means keeping the element or dropping it. Keeping, dropping. Or it can map it. This is signified. And in the implementation, that's this branch. So the result is a spec as a union of element and value. It may contain the original elements or the replacements, and the spec does not say which. That's sound and coarse. The dependency between the shape of your predicate and the shape of the result is lost. Concretely, if my predicate always returns a text string, I am still handed a list that might contain integers, and I have to case over every element to get rid of them. Losing preciseness means the solver has a more difficult time to prove type safety if you apply the function. Applied on a list of atoms, for example, the transformation of strings is lost. If you expect a list of strings, the solver can't prove this and will flag this application as a type error. Instead, let's make the type specification more precise. 3 arrows separated by semicolons, a Boolean predicate that gives you just t, a predicate that if you only ever tag things gives you u, and a mixed one gives you the union. For the solver, this is one type, the intersection of 3 arrows. The implementation is checked against all 3 independently, and it passes all 3. Body does not need to change. Now, when we apply a transformation only, we can precisely reason that the output will be a list of strings. The output will be a list of strings. Next, what interesting things can be found when we enable exhaustiveness by default? Let's look at some bugs that we found. These are 2 lines from our own constraint solver. We have 3 occurrences of the variable st2, which is supposed to thread the state through our solver. The first one binds, the second one does not bind. It is a match against the value that is already there. So this line quietly asserts that normalize returns the state it was handed. If it ever returns a different one, the process, which means the whole solver, crashes with a bad match. What was meant was to thread the updated state through, of course. So basically, I made a counting typo, and this was unnoticed for as long as the code has lived, basically. Why did we find this? Well, internally, the match operator is transformed to one clause case expression, and both the formal theory and the implementation have exhaustiveness checking enabled by default. So here the clause for ST does not match is missing. Subtract what the single clause accepts from the input type, and the remainder is not empty. So an exhaustiveness issue. This is what negation types gives you at the meta level and how they're used inside the solver. Next, our binary decision diagram structure lives in a header file included by half a dozen modules, each instantiating the BDD with its own leaf type. So basically, C-style compile time polymorphism. Here, the unparse function matches on the leaf values 0 and 1. When the leaf is a bool, that is correct. Its type is 0 and 1. When the leaf is something else, 0 and 1 are not inhabitants of the leaf type at all, provably. These two clauses can never match, and the checker flagged them as dead code. The implementation was not wrong, but we missed a short circuit optimization in exactly the modules where they were dead. And for now, a nice example from OTP itself. This set is spec'd for every term and it has a catch-all clause, so it looks total and it should be total. When something is total, we are of course permitted to supply any value the language permits. This includes the seldomly used improper lists, as they are called in Erlang. These are lists with a different termination other than the empty list. For example, this here terminates with the value 1 and is an improper list, and it matches this pattern perfectly well. And the two argument helper functions below, those are only defined for proper lists. So the function crashes where it promised a boolean. This has been in the standard library for now 16 years untouched, and it passed dialyzer and equalizer. So two things hide it. This pattern matching for lists is overloaded in the language. It matches for both proper and improper lists alike, and even if you wanted to guard against this by refining with the isList predicate, you cannot. The isList predicate filters not for lists, but for improper lists, since you'd need to traverse the whole list to determine if a value is a list or not. Internally, this is the same mechanism as the previous bug. Input type minus the clause, remainder is not empty. We had, of course, difficulties when type checking our type checker. First, we treat type specification as truth. This is a problem when A, the specification is not yet verified against its body, so potentially wrong, and B, when the specification is verified against its body, but too imprecise to be useful. Let's look at often used functions. List map is fully polymorphic in the standard library. A goes in, B comes out. This is as precise as the solver needs it. In contrast, let's look at folding. Folding says term 4 times. There's no relation between the accumulator you pass in and the value you get back. Problem is, you have to narrow it manually before every single use. Not one downcast at the call side, one at every use side downstream. These specs were written as documentation and as input for dialyzer, whose success typing reading is a different thing entirely, and they cannot change them without breaking that. Therefore, every Erlang type checker has independently built the same escape hatch. Equalizer ships replacement specs for over 100 functions per OTP version, and we ourselves needed 42 overrides. And this will only increase as more code is type checked. So as a takeaway for languages that are transitioning or trying to transition to gradual typing, the better your type specs are, especially in standard library, the better it is for the community, both users and type analyzer developers. One thing, when there's no static type, when no static type is available, we have gradual typing. Currently, it's used for specless functions, of course, and for the message passing part. Here, for the receive expression, the type of what arrives depends on the protocol between processes, and no Erlang type checker tracks that today. So until message passing becomes first class, dynamic is the only treatment. The second one is from OTP's JSON module. For encoders that recurs over subvalues of different types, type theory is limited, saying that statically needs rank 2 polymorphism, and we only support rank 1 polymorphism. That's why dynamic is used here. In our code base, we've also encountered this once, where we generically traverse and map any value given, and rank 1 polymorphism is just not enough to describe this. To summarize, what did it cost to take 6,000 lines that already ran in production and make them verify? Well, we touched about 1,200 lines of code, a fifth of the code base, and most of that is type annotations themselves, or painful architectural changes because of fixing hacky data structures, bad encapsulation, or just less dynamic evaluation in general. For us, this trade-off was definitely worth it, as the guarantees we are now given outweigh the costs. We have 42 spec overrides, and we only needed 24 downcast escape hatches, and most of them at the boundary of a database, basically. The reason we argue that exhaustless should be on by default here is how often we need to explicitly opt out of exhaustless checks. This is the thing people expect to hurt in a let it crash language. Across both code bases, we ran just above 2,200 exhaustless checks, and we only needed 46 opt-outs, 2% roughly. And in most of those cases, the intentional partiality was already documented in a comment right there. So that tells you this basically property of the function the programmer already knew about. During the type checking, we had to split big functions into smaller ones. So we had 29 really big functions, spanning over 15 function heads, and we had to split 7 of them. Occurrence typing is exponential in the worst case, and at the time we could not check a 35 function clause dispatching on a 25 union alternative. We split that into 17 smaller ones. That scaling problem has since then been fixed or lessened, but the split function still lives in our code base. And this is the result. Our core library is verified. 5 standard library modules are also verified. We have 0 timeouts, thankfully. For a long time, set-threaded type checking with everything switched on was assumed to be too expensive for this. Time-wise, we have a 1/10 of a second per function on average. The worst single function takes 6 compared to minutes and many timeouts before. For scale, we have Dialyzer, which takes 100 seconds cold on our code base and 30 seconds warm. And Equalizer here does it in a few seconds. It's doing less, but it's really, really fast. 3 things we would tell language developers that try to transition to more static typing in their dynamic language. 1, prefer code that the checker can see. Prefer static over dynamic. 2, write the spec you mean, not the spec your tool tolerates. And 3, standard library specs are infrastructure, or should be infrastructure. For us, Erlang types is the first substantial project we have verified outside the standard library, and our next goals are, of course, getting to the message passing world, GenServer, GenState encode, and these are our next targets. Thank you, and I'm happy to answer any questions.
Okay, thanks to our pre-recorded speaker. And if you have any questions for them, you can maybe reach out to them, and we'll wait until next time.
Yes, I can see everything. It's perfect.
Are you plugged in? Okay, there we go. So next we have mode crossing, talk given by Benjamin Peters. Thank you.
Thank you. This is joint work with colleagues at MPI-SWS and at Jane Street. Mode crossing is part of Jane Street's OxCaml project, and specifically an attempt to make it more usable in practice. So let's talk about that language first. OxCaml is a set of backwards compatible extensions to OCaml used and developed by Jane Street. And one of the features OxCaml provides is it uses so-called modes to track additional program properties as part of the type system. The kinds of properties it tracks are things like locality, affinity, and uniqueness, but also things like purity. Oh, well, that's sad. This is supposed to change. I can remove this and plug this back in.
It's changing on your end.
It's changing on my end. There should be nothing over there.
Plug it back in and something on.
I'll plug it back in.
Or it seems like there's some kind of delay.
Yes.
I'm moving things on my end, but nothing's happening here.
Yeah, something slow is happening over there because I just sent color bars and it didn't show up.
Okay. I'll try again.
Nice. Yeah, that's moving. Cool.
Amazing. Let's try this again. One of the things OxCaml does is it. Wait, no, this is wrong. I can't talk like this. I'm just praying I'm not breaking it again, but okay, this is better. I can see my notes now. OxCaml uses so-called modes to track additional properties as part of the type system. And one of the things it tracks is thread safety, which is going to be the set of modes that I'll use for the sake of example in this talk. So how does OxCaml use modes to ensure thread safety? Here's a little example program. What it does, it creates a function f with some internal state x. And every time you call this function, it increases the counter stored in this internal state by 1 and returns the current content of the counter. And then what we try to do is we use this fork join construct to run this function twice at the same time in different threads. Now, this is a textbook example of a data race. And OxCaml claims to prevent these kinds of data races. The way it does that is it annotates all variables as either portable, so as thread safe, or as non-portable, so as thread unsafe. And clearly, the function f that we have here is going to be inferred to have the non-portable mode, because this is not a thread safe function, so it's not safe to call this at the same time from different threads. The way that OxCaml detects that is by looking at the definition of the function itself and seeing whether it captures any external state. If a function captures thread unsafe state, like the variable x, then it itself is thread unsafe. And then in the next step, OxCaml is going to report, oh, f is non-portable, but it should be portable because we try to pass it to this fork join function that requires its arguments to be portable. So now let's actually take a look at another example. Here we have a little stack module. The stack module exposes in transparently some type constructor alpha t, as well as two functions to operate on this type constructor in like a stack-like fashion. We can allocate an empty stack, or we can push a value onto a stack. Now, let's also suppose we have a function send. This function send just takes anything and sends it to another thread. We don't really care about what it really does. What's important to us is that it requires a portable object. Now, let's say we tried to create a stack. Let's say we tried to create an integer stack that just contains the number 0 and send it to wherever it wants to go. Now, this program fails to compile in OxCaml, and that is very sensible. We have no idea how stack.t is implemented. It might contain mutable state, and so it might be unsafe to send it to another thread. But what if we did know how stack.t is implemented? What if we did know that stack.t, that this type, is implemented as your standard type of immutable lists? Then, if we had the send function, and if we created an integer stack, then it really should be okay to send the stack.t to another thread. This is an immutable object. There's no way that sending it to another thread can cause any issues. To realize this as part of the type system, we can observe that values of this type, values of type in stack.t, are in some sense always portable. They are always thread safe, no matter how we created them. And in this case, we say that in stack.t crosses, or it mode crosses, the portability axis. Now, in the example we saw before, we don't actually know how stack.t is defined. Like, we deliberately had this intransparent stack signature, this intransparent module signature. To make that case work, we somehow have to declare the mode crossing behavior of the type as part of the public interface of the module. And the way we do that is with the so-called modal kind, which is this value mod portable with alpha we have up there. So, and with this modal kind in place, the program we saw in the beginning does actually compile. So let's take a closer look at the different components of this modal kind. A modal kind consists of 3 parts. It consists of, at first, of a layout, which is in this case value. Layouts are part of an orthogonal OxCaml feature, so this is always going to be value for the purpose of this talk. The second part of this modal kind is the base kind, mod portable. It describes what axes are crossed in principle by this type. The stack.t type that we saw before does not add any new thread unsafety to whatever it contains, so it can, in principle, cross the portability axis. However, the mode crossing behavior of our alpha stack.t's also depend on what alpha is. This is expressed by the width bound with alpha that says you can only cross the modal axes that are also crossed by alpha. In words, this kind expresses that stack.t crosses portability only if alpha also crosses portability. At the moment, there are more than 10,000 modal kind annotations in JStreet's codebase, and the adoption of OxCaml as part of the code was considered entirely infeasible without this feature. We present a design of OxCaml with both mode crossing and with modal kinds, along with an implementation as part of OxCaml, including the theory that we needed to come up with to implement an inference algorithm for modal kinds. We also have a formal representation of this entire calculus, along with the soundless proof in Rock and Iris. Now, before we get to the theory of all of this, let's take a step back to look beyond the single axis, to look beyond just the portability axis that we've been using. Because OxCaml has a lot of modal axes. For the purpose of this talk, we'll just focus on 2 of these axes. We'll focus on one hand on the portability axis that we've already seen, that is used to track the thread safety of functions. But all values are also annotated with modes on all of the other axes. The other axis that we'll focus on in this talk is the contention axis, which is used to track the thread safety of mutable state instead of functions. The details of how portability and contention actually interact are unimportant for the purpose of this talk. This talk is really about the mode crossing behavior of the types themselves. In the remainder of this talk, we'll answer 2 questions. On one hand, how do we represent and think about these modal kinds that you've seen on the previous slide, which turn out to be easily representable using so-called kind functions. And also we'll discuss how do we compute with these kinds And it turns out that these kind functions have a normal form that is useful for working with kinds. So let's try to answer the first question by looking at a few more examples of concrete types and their modal kinds. Consider, for instance, the integer type. Integers have, in our case, type a kind value mod portable contended. They also cross all other modal axes, but we're just focusing on portable and contended now. The product type, alpha times beta, has kind value mod portable with alpha with beta. So they cross portability and contention in principle, but only if both alpha and beta also cross these axes. Alpha ref, the type of mutable references, has kind value mod portable with alpha. So it does cross the portability axis, if alpha also does, but it does not cross the contention axis, because that's what actually used to track the thread safety of references. But, well, so what if we try to compose these types? So what is the kind of, say, alpha ref ref? Well, what we can try to do is we can take the kind and type of alpha ref and substitute alpha for alpha ref itself, and we can compute that alpha ref ref has kind value mod portable with alpha ref. But that doesn't really get us very far, because we're now stuck. We don't know how to unfold the alpha ref at the end of that kind, because we've really only seen the syntax for kind. We haven't yet specified what it means. So let's do that. Intuitively, the kind of a type is represented by the set of modal axes it crosses. So the kind of a concrete type is just a set of axes. It might, for instance, be the set that contains the portability and the contention axis. Then, the kind of a type constructor, which is essentially just a function from type to type, is a function from kind to kind. For instance, if we recall the kind of alpha ref, which is value mod portable with alpha, then the kind function that represents the modal, that represents this modal kind, is the function that maps the input kind alpha to the set that just contains the portability axis, representing the base kind mod portable, intersected with the kind alpha hat, telling us that this type crosses the portability axis, but only if alpha also crosses that axis. Now, I should tell you that the system that we present in the paper looks different because it flips the lattice that we're working with, and it actually works with a more complex lattice to be able to handle more complex modal axes. Now, while this representation of kinds as functions makes inferring the kinds of concrete types relatively straightforward, even when you have recursive ones, what happens if you have types whose identity you don't actually know? Here we have another example where we have this module type T1 that just contains some type constructor alpha T. Then we're declaring a functor, in this case the double functor, that gets as an argument this module M. Essentially, this module M just contains some type constructor alpha T. So this functor is given some type constructor as its argument. Then within this functor, we're defining a type, alpha double M. This type is defined as containing an alpha m dot t m dot t. So it contains two applications of the type constructor that we were passed as an argument. Now, in this example, we also annotated this type with a precise kind, and specifically with the kind that ends on with alpha m dot t, just one application of this m dot t type constructor. And what the compiler has to do here is it has to check whether the inferred kind for alpha double m is a subkind of the one that we have annotated as part of this type declaration. However, the subkinding check has to be executed in the presence of an abstract type. Intuitively, the subkinding check on kind functions is just some kind of point-wise check, but how do we do this check in the presence of abstract kinds? We have to somehow determine subkinding over abstract types in our context, for all abstract types that this could ever be instantiated with. And in fact, dealing with abstract kinds this way is where most of the implementation complexity of the system actually lies. So How do we deal with that? The key so somehow it feels like we need to develop a better theory on the behavior of kind functions. The way we do that is by observing that the kind functions that we have in our system have a certain normal form. So here, recall the kind function that we saw for the alpha ref type earlier. The normal form for kind functions look as follows. It's determined by two constants, C0 and C1. The constant C0 represents the contribution of the base kind as part of this kind function. So this is really just the set that contains the portability axis here. The constant C1 represents the contributions of width bounds, and the contribution is specifically of alpha as part of width bounds. In this case, we'll choose C1 to just be the empty set. There are other language features that I haven't shown to you today where this set has more interesting behavior. Now, to check subkinding in the presence of abstract types, we proceed as follows. Somehow, if we simplify it slightly, the compiler must decide kind equations, that's to represent subkinding, in the presence of unknown kind functions. So to simplify it a bit, it would have to check whether the width bound with alpha m dot t is less or equal to with alpha m dot t m dot t. We can write this as a statement over m dot t's kind function. So let's call it f. Then the statement we would get is that for all alpha, f of alpha is less or equal than f of alpha hat. To decide these kind of statements, what we can do is we can represent f in terms of its coefficients symbolically. So we're treating these coefficients as unknown variables, x0 and x1. And by setting up a bit more theory and by being clever how we interpret these symbolic equations and how we simplify them, we can actually type check the example that we've seen before. And this weird subkinding with one or two applications of m dot t does actually type check using this symbolic subkinding check. So this was an introduction to both mode crossing and to modal kinds. In the paper, you'll see how we support more type system features, such as non-uniform recursive types, such as n-ary type constructors instead of just unary ones, but also things like more complex modal axes and modalities. That's a mode-specific type system feature. We also talk a bit more about how we implement the system and how this symbolic check works. And we talk about how we prove soundness of the system in Rock and Iris. Thank you.
Any questions? People want to come up to the mic?
Hello, I'm Dimitri. I had one question. So yeah, with the stack example, does it check, like when in type checking or kind checking or whatever you call it, does it check that the implementation matches the declared mode? Like you mentioned, it checks that the it's a subtype of what's declared, but like if, say we had a stack that, was implemented with mutability or something and didn't have the portability or something like that, is that something that it would check at compile time?
Yes. So when you have this module signature up there, then you also instantiate this module signature, and the compiler would check, do the types that you have declared actually conform to the kind, to this modal kind contract that you've declared as part of the module signature.
Great, thank you.
This is a quick question. I was a little bit confused at the condition that A had to cross the mode portable. So for instance, if I had a stack which has this condition and A does not cross portability, but A happens to be portable in this context, would that stack not be considered portable then?
That's a very good question. That you would model in XCaml using this modality mechanism. So you would wrap your alpha in a portable modality, and then that would cross portability.
Okay, so you would just make the box on it.
Yes, exactly. You'd use a box type.
I would like to have a question related to the entire extension thing. Do you plan a similar extension to Rock, or is it needed there?
So modes are specific to XCaml. I do think that the mechanism that we've come up here does potentially generalize to other systems, but this is inherently tied to some notion of mode or some notion of modality.
I see. Thank you.
Thank you very much, Benjamin. Next, we have Alexander talking about a separation logic for parallel time complexity with work and span credits.
Okay, so hi everyone again. My name is Alexandre Moine. I'm a postdoc at NYU working with Sam and Joe, but it's actually my last week at NYU because I'm an incoming researcher at INRIA Lyon. All right, so today I'm going to talk about a separation logic for parallel time complexity with work and span credits. Let's jump on an example. Here we have a parallel program that makes use of a par primitive. Par primitive takes two closures and evaluate them in parallel and return their result as an immutable pair. And here in this example, we take three int lists and we are going to compute their sum in parallel. So we fork two tasks, one that computes the sum of xs, the first argument, and then another one that will fork itself two tasks, computing the sum of ys and zs, adding the result, and then again adding the result. So if we want just to represent the parallel composition of this program, we use what we call a computation graph, where each vertices is sequential unit of computation, two outgoing edges are a fork, and two ingoing edges are a join. So this program here is represented by this computation graph. And the question here is how much time does example take on P processor? And actually this parameter P is a bit painful if you want to make the proof or prove a result about the time complexity here, because you don't know really what P is and if you have enough processors to schedule all the tasks or not. So an idea is to abstract from this number of processors. So we do that, and we annotate the computation graph with a few more information. So each task has a task identifier, Ti, and then a cost. Here we're analyzing the number of additions made by each task. So the three parallel tasks here have the length of the list additions, and then the joining tasks each do one addition. And on this graph, we define two metrics. The first one is called the work. It's the total weight of the tasks in the graph, so it's a total number of operations, and intuitively it's a cost, the time complexity on the single processor, because if you only have a single processor available, you have to actually compute everything. And then we define the span. The span is the weight of the heaviest path. So here, if you say that ys is the longest list, then the heaviest path will be something like that. And it represents the time on an infinite number of processors. Indeed, if number of processors is not an issue, you can consider that everything happens in parallel, and the time you're going to spend is really the longest dependency chain. So with work and span, the cool thing is that you can actually bound the time on P processors using the Brent theorem. So with an adequate scheduler, a computation with work TW and span TS can be executed in time TP with P processors, such that TP is bounded by TW and TS. And this bound is actually realistic. A lot of schedulers actually get close to this bound. So now my initial question refines, and the question is how to formally verify work and span bounds. So in order to address this question, I here put the word formally, so we need a cost model, or a way to describe which operation we account for. We do that with a ghost operation called tick. So we instrument programs with a tick operation that will mark unit of time that we want to account for. So we have a ghost function from unit to unit, and for example, we can modify the list sum function to have a tick operation before each addition. So if we bound the number of tick, we bound the number of additions to the program. All right, so now the question is how to account for the number of ticks in a program. And actually, it's a well-understood problem in a sequential setting. We use what we call time credits in sequential separation logic. So the idea is that we have n dollars here, which we call time credits, that will allow to perform n tick operations. The idea being that if I'm able to verify the program E, So this is the weakest precondition. So if I'm able to verify the program E under the precondition of capital N time credits, then any execution of E has at most n tick operations. So the time credits allow to bound the number of tick operations. How do they work? Time credits are additive, so if I have n plus m time credits, I have n and m time credits. And if I want to verify a tick operation, I have to spend a credit. So using these two rules, you can perhaps see how we derive this soundness theorem, that if I'm able to verify E with n time credits, I bound the number of tick operations by n. So now the question is more, can we generalize time credits to work and span? Does it scale to parallel programs? The answer is yes, of course, I'm here today. So we contribute Sparkas, a separation logic for work and span. Sparkas comes with work and span credits. We verify several examples, parallel prefix sums, parallel merge sort, treble stack, soundness theorem, and everything is mechanized in rock on top of Iris. A hint at the name, Parkas is a Spanish translation of the three fates, the Greek goddess that measure the threads of life of everyone in parallel. All right, so let's go back to work and span credits. So work and span credits. Work credits, we write them WN, and it's a permission to perform n tick operations anywhere on the computation graph. So intuitively, work credits are your standard time credits. The new things are with span credits, which we write STM, and it's a permission to perform n tick operations on any path from T. So it bounds the heaviest path starting from T. Because we annotate span credits with task identifiers, we need a way to reflect task identifiers in the logic. So we annotate the weakest precondition itself with a current task identifier T and an end task identifier T prime. And the soundness theorem of the logic is what you would expect. That is, if I'm able to verify the program E at initial task identifier T0, then if I'm able to verify this program with n initial work credits and m initial span credits, then any execution of E has at most work n and span at most m. So now what are the rules that govern these credits? So splitting is as usual. So again, if I have n plus n1 plus n2 work credits, I have n1 and n2 work credits. And if I have m1 plus m2 span credits, I have m1 and m2 span credits. Nothing new here. And tick is also quite expected here. So to verify tick on the task T, I have to spend one work credit and one span credit for T. And in the post condition, I learned that the task identifier didn't change because tick is sequential and the return value is the unit value. So now comes the interesting rule. What happens when we update these task identifiers? What happens on a par? And the key idea is that we are going to duplicate span credits. So this is a headline that should scare you in the world of time credits and credits. You are not able to duplicate money, but let me show you how it works. So here, if I want to, this is a rule without credits at all, because it's already a verbose rule. It says that to verify par of E1, E2 at task identifier T, I have to verify E1 and E2 at some universally quantified task identifiers T1 and T2. And in the post condition, I learned that the n task identifier is T3, and that there exist two n task identifiers T1 prime and T2 prime to n value V1 and V2, such that the par itself returns V1 and V2, and we have the post conditions of E1 and E2. So describe really this graph here. And now I said that we are going to duplicate credits. So what happened? We require the user to give n span credits for T, and we duplicate these time credits, these span credits, so we give n span credits for T1 and n span credits for T2. Intuitively, that's why we encode the max here. We say that if the heaviest path from T is bounded by n, then the heaviest path starting from T1 is bounded by n, and the heaviest path starting from T2 is also bounded by n. All right, so if you follow closely this talk, I explain how to transfer credits from T to T1 and T to T2, but how to transfer credits from T1 prime to T3 and T2 prime to T3, how to close here. Or the question is more, can we transfer credits to the continuation? So how to transfer credits even from T to T3. And the standard answer to this kind of question in separation logic is the most beautiful rule of separation logic, the frame rule. So usually when you want to transmit something to the continuation, so an assertion phi here that you currently have in your context, you can use frame to transfer the phi here from before the execution of E to after the execution of E in the postcondition here. The issue is that we cannot use frame directly here because if I just instantiate phi with STM, I can actually use frame, but I will end up with potentially useless credits in my postcondition here because T might not be equal to T prime, especially if I did a fork and join. So we just purely fix this rule using a transfer rule. Transfer is exactly the same rule, except that this time we update the task identifier and we obtain a span credit for T prime in the postcondition here. And really, that's all you need to verify actual programs using Parcas. So here is a small example of a program we verify. It's the infamous parallel for loop. So par4 takes two bounds, A and B, and a function f that par4 is going to execute in parallel at each index between A and B. The function is defined inductively. If b minus a is less or equal to 0, return the unit value, there is nothing to do. Otherwise, if we have only a singleton element to do, we just call f. Otherwise, we compute the middle point. We do a tick operation to account for the recursive step, and then we call ourselves recursively on the two ends. So it really gives rise to a binary tree here. And I'm insisting on the binary tree because it will show in the bounds. So again, what is a specification of par4? So this is a standard specification of par4. If I just specialize A to 0 here for simplification, well, if I have to verify par4 between 0 and B for f, I have to verify calls to f at any possible index I between 0 and B at some task identifier T prime. Then for work credits here, so notice that I have a tick at each node in the binary tree, and the number of nodes in this binary tree are b minus 1. And then I have n times b. I have b leaves in this tree, so I have to give n times the work bounds that I'm going to give to f. And interestingly, then it's for the span credits, because for the span, you can see a log parameter that appears. The log comes from the height of the tree. And then you have m span credits that are going to be duplicated for all the tasks you run. So we give m span credits here for the calls to f. All right, there is more in the paper, in particular more relaxed rules for transferring span credits. You don't need to use this bundled transfer rule. We have a soundness proof, of course, and we verify several examples, in particular parallel prefix sums, also called scan, and a parallel merge sort. And I think it's the first time we mechanized the time bounds for parallel merge sort, because this proof was actually quite difficult to do, and we needed some LLM to figure out how to close this bound. We also verify Trebor's log-free stack using concurrency, and it's a fun experiment because Trebor's stack is subject to contention, so you can evaluate multiple operations of the stack in parallel, but due to contention, you might have to sequentialize everything. So the best bound we can prove is the work is equal to the span, so you don't win a lot on the worst case in using Trebor's stack. All right, so I presented the separation logic with for parallel time complexity with work and span credits. The key ingredients are work credits, which are a standard technique, and span credits, which are new. Span credits are annotated with a task identifier. Par duplicates span credits and transfer moves leftover credits to the continuation, and everything is mechanized in Rock on top of Iris. As future work, we would like to target less structured parallelism with futures, for example, and also probabilistic bounds, because work and span bounds are often given with high probability or in expectancy, so we need to adapt the logic to cater for these probabilistic bounds. Thank you.
All right, thank you very much. Questions? Come up to the mic.
Hi, thanks for the talk. I was wondering, so you had in the post condition of the weakest pre that you can have a new task ID, and that of course makes sense for the fork rule, but why do we need a new task ID after joining?
Because we mimic the computation graph. Here, just the graph we define our metric in is defined using this new task here after join point. So we need to reflect it in the logic.
Any other questions? Okay, let's thank our speaker again. Okay, next we have localmem, type-directed adaptive serialization for location and content addressable memory. Take it away, Michael.
Thanks. Okay, so functional runtimes normally make us choose between compact values or cheap sharing. Localmem is a type-directed memory model for getting both. And the same discipline works in two kinds of memories, one local and one content addressed. So to start, let's take this small tree. A conventional runtime allocates each node separately and assembles the values with pointers, as on the right. The payload is tiny. Much of the representation is boxes, headers, and links. A traversal follows those links wherever the allocator happened to put them. But the cost that's really important for this talk appears when the value leaves a process. So these heap objects are not transferable bytes, of course. We have to walk them, encode them, and later rebuild them. In other words, heap form and wire form are different, and we have to pay for translating between them. So take the same value and lay its tokens out contiguously. Now the representation itself is dense. There's no per node headers or pointers, and a traversal becomes a linear sweep through memory. But here's the main benefit. These are not bytes that we later serialize. They're already the value's native heap representation. We can send them over the network, write them to disk, map them to another process, and the value moves by a plain copy. So the heap bytes are the wire bytes. And in the spirit of local, that lets us bring the program to the data. So have we solved our problem yet? No. Of course, a functional heap has to share, and this kind of flat representation apparently can't. So suppose T is a billion node tree, and the program builds one new branch above it. In an ordinary functional heap, this operation is constant time, and the new node points to T. A completely serialized heap has only one alternative. Copy the billion nodes to a new stream. And that's not a viable semantics for ordinary functional programs. So the heap cannot stay completely flat. But what we want to do is keep values dense, except where sharing demands a pointer. That design point is mostly serialized memory. It means serialized bytes as the native heap with selected indirections. Gibbons spent a decade building toward this design with the compiler, typed layout IR, parallelism, and a real garbage collector. The missing piece in this picture is a specification for the adaptive serialization that's going on underneath the garbage collector. So our idea here is to let the type decide where sharing may interrupt the value stream. We call an eligible type a boundary data type. So at an iTree boundary, the runtime may keep the subtree inline or replace it with a wrapper that points somewhere else in the heap. We formalize this choice and mechanize its meta theory in Rock, and it gives us bounded sharing costs and also supports our efficient content address memory model. So why should types control this? Because the type in our model already tells us how to read the heap. So start at an iTree. A tag says either leaf or branch. Branch's type says the next field are a uint and two iTrees, so we read them in order. The headers didn't vanish. The information just moved into the type. Only a jump needs extra data. This green 8 is the heap index where the right child begins. So it skips the whole left subtree. So tag goes to constructor, type to fields, skip index to jump. That's the overall economy of locale. The format stores only what the type cannot know. But sharing requires some kind of pointer. So where can that live? Not directly in a raw type. A pointer type would make every iTree indirect, and that would permanently block a dense representation. So instead what we do is extend the data type itself. iTree gains a third reserved constructor called PTR there, which takes a pointer and still produces an iTree. So indirection is now a value level choice. The subtree here is shared. Now consider changing that 9 value in the tree to a 10. The new spine keeps the unchanged sibling by placing it behind that constructor. The wrapper now costs 2 tokens, a tag and a pointer, and it buys us constant time sharing. But the strip is no longer one dense run. The heap is now fragmented, exactly what the collector must repair later. So where may those pointers appear? Let's consider both extremes. We could wrap every type, and every value then gains an alternative pointer constructor, but then one constructor records lose their free tag, and every read has to check for indirection. So at the limit, we've rebuilt the pointer heap we started from. On the other extreme, let's consider wrapping no type. Then sharing must copy until it reaches a boundary. But there is none. Sharing a list tail, which is ordinarily constant time, becomes linear. So placement here determines the cost of sharing to some extent. The quantity we want to control is the distance from any value to its nearest boundary. So that gives us the invariant. Assign boundaries so that every unfolding reaches one in a bounded number of steps. For iTree, recursive fields are boundaries, so every path reaches one immediately and the wrapper always fits. However, if iList were inlined, its con spine would unfold forever, and at no point on that spine could we share without unbounded copying. So in the paper, our concrete usable placement rule marks one constructor bounded size types as boundaries, but there's nothing that would stop one from constructing a number of other different placement roles. This one's just sufficient but not unique. Now, in general, call the resulting static copy bound maximum duplication size, or max dup size, of a given type, tau. Every shallow copy stops within that many tokens. Now, this locale economy appears a third time. So an unknown size buys a skip index, an unknown constructor buys a tag, and sharing beyond the types bound buys a wrapper. Okay, so this wrapper fragments the heap. Evacuation repairs it. On the first time evacuation visits a target, the collector follows the wrapper and writes that subtree inline. However, if another wrapper reaches the same target later, it keeps the wrapper so sharing is not duplicated. The collector is largely traditional except for this step. Evacuation reserializes while it copies. The result is dense again without changing the program's value. That reversible movement between inline data and wrappers is what we call adaptive serialization. Now, a wrong splice can still look like a valid heap. Valid tags, readable bytes, wrong value. So byte for byte equality is also the wrong specification because changing representation is the collector's job. We use two observations. Materialization says what value is written at an address, leaving wrappers visible. Deep equality says when two such values are the same to the program, ignoring inline versus wrapped and physical location. So in this diagram, follow the square. We materialize before and after evacuation, and the results are still deeply equal. So this is the main theorem that we prove. It shows that evacuation preserves the value and doesn't care about the representation. We proved this theorem in ROC, among others. Okay, so every pointer so far names a region and an offset in one store. But if we move the bytes elsewhere and then that name dies, even though we serialize the representation itself, even though we serialize that representation, and it moves by plain copy. A content pointer is a value, angle bracket d comma I, of type CAPTR tau. The digest D names canonical bytes, and the offset I selects a value within those bytes. Because D is computed from content, the same value receives the same name wherever it lives. Git made this idea familiar at an enormous scale, and so did other tools such as IPFS. So now we have two memories governed by the same type discipline. Location addressable memory, the first one, inside one process, and content addressable memory for values that can outlive it. A content name turns several operations into name comparison. We have integrity, caching, deduplication, and up to the hash assumption, deep equality. We have a commit operation that, of course, commits canonical bytes to a digest, and a dereference that fetches and decodes them. But every digest consists of 32 bytes, and computing one traverses the whole content of the value. One digest for a whole value, which could be arbitrarily large, minimizes metadata but rehashes everything after an edit. One digest per node localizes edits but creates big O of n digests. The original idea of this kind of content addressable memory comes from an authenticated data type paper by Miller et al. And this idea made this content addressable type constructor first class, proposed this idea for functional languages. However, in this paper, what we consider is an extension of this idea where we ask two additional questions. Where may the runtime cut values, and which candidates should actually fire? So boundary data types answer the first question. Every boundary constructor has a potential chunk point with gaps bounded by max dupe size. The mechanism is from the first half. The declaration of each type gains now a second reserved constructor, what we call CPTR, and that carries a content pointer and a policy. We also have a policy that decides which candidates fire. The one we analyzed tests two subtree local predicates. A rolling hash distributes cuts by content, and a deterministic cap forces a cut when the residual exceeds C. On a cut, the subtree is replaced by a CPTR constructor in the parent tree. Every decision is subtree local, so equal subvalues produce the same chunks and digests. This boundary discipline is the reusable abstraction here. It consists of a hash plus a cap in one policy whose properties we prove in the paper. I'm going to, now consider an edit at of a value at a depth D. This path has to be rebuilt. Sibling subtrees remain untouched. We count changed chunks in spillover. Now, untouched constructors are retraversed because they share a chunk with the path. For a balanced tree with kappa and C both equal to log n, the expected number of changed chunks is constant. And the expected affected constructors is big O of log squared n. So at roughly 1 million nodes, this theorem says that at most 5 expected changed chunks and 400 expected affected constructors. We formalize this locality theorem in Lean 4 with mathlib. Let's skip this one. So to wrap up, serialized data can be the heap, provided that the type says where indirections may appear. Locally, pointer constructor carrying a region and offset makes structural sharing cheap, and collection restores density after the fact. Globally, the same boundary types supply typed chunked predicates, typed chunked candidates. For one hash plus cap policy, we prove and mechanize a strong locality theorem. The memory models and their proofs are mechanized in ROC and Lean, and the evaluated artifact is available. So we have one discipline of boundary types with 2 different types of memory that we formalized here. Thanks for your attention.
Any questions?
Hey, Mike, nice talk. It occurs to me that this gives us a way of working with chunked data structures perhaps like more easily than previously I was wondering if you could just comment on that a little bit.
So it effectively, the content addressable part at least automatically produces a chunking of a value of any type. And that chunking has nice locality properties that we go into detail in the paper, but yes, so essentially it's doing that automatically. It could probably generalize beyond content addressable memory. Yep.
One of the original hopes of work like Gibbon, as I recall, was to by reducing the memory footprint of our functional programs, we could also increase how quickly they ran. To what extent is that still in the dream in a system like yours?
Yes, so we in this work, we took the implementation of Gibbon as a starting point and formalized it in this model. We didn't run any experiments But all of the assumptions that are present in the original Gibbon implementation are present in the proofs. So the efficiency properties should hold over if it's implemented well.
Hi, Aaron Su from Dialogue. I guess you may have answered this question already, but have you implemented this down to the bits, and do you have any comparisons against other linearization forms of trees? And like one thing that came to mind was, it looks like you're still using generalized pointers to manage this stuff. Have you looked at controlling the trees into known regions to control the pointer size and allow for append-only operations in the trees? And have you done any comparisons on how much space you're actually saving or not, depending on your heuristics?
So the original, there's a series of Gibbon papers that had done some extensive performance analysis. There's with an implementation. The most recent one was at ISMM. It's on a garbage collector, a generational garbage collector. Some of the properties of that one are the ones we formalize here. The comparison in that one, if I'm remembering correctly, there was comparisons with GHC and Java, I believe. There's been some follow-up work as well. Sorry, the second part was, do we consider alternative representations of pointers? To my knowledge, there hasn't been any consideration of that in the past work on Gibbon.
Okay, and then another question of, have you compared against non-garbage collected approaches for this?
Oh yes, yeah, there was some, not in this work of course, but there's been at least a few of the Gibbon papers that compare with C. That's usually the baseline in all of those papers, if not always. Yeah.
Okay, let's thank Mike again. And enjoy some coffee.
session. First off, Garrett Morris is going to talk to us about yet another type inference algorithm.
I actually left yet out because it felt pretentious. I was going to use slides. It's
yeah, plug it back in. I think just the AV needs to switch it over. You see it on your end, right?
all right. It's fantastic. So yeah, so I want to tell you about another type inference algorithm, but I want to start out by telling you what I'm doing up here, because as a rule, I like to work on problems that nobody else cares about. I get cited less, but I get scooped a lot less. But here I am working on a problem that's not only still of active research interest. I mean, there have been other papers on this topic at this venue. So I want to start out by trying to explain what went wrong. And so I've been working on one of these things that nobody else cares about, a functional language for extensible data types. So sort of like records that get smaller and variants that get bigger. It's based on a core calculus called R omega. And this language happens to also have first-class polymorphism. And I would like this first-class polymorphism to be implicit. So I keep having to write terms like this, or I keep having to infer types for terms like this. Now, this just looks like a pile of applications, because this is just a pile of applications. But let's look at the types to see what's interesting. Okay? So this first thing, cell K, this is the generic selector for the K-labeled field of a record. So if you look at its type, essentially what it's saying is, you give me any record, that's the pi z part, and I'll give you back a T so long as the structure of that record, that's Z, happens to have K labeling T, right? So I don't care what else is in the record. I don't care what T is. Just so long as you give me a record structure that's got label K, I'll give you back the thing that's associated with it. In practice, we have first-class labels, so it's a little more complicated, but this is sufficient. Now, D had then better be a record, and because I'm going to keep applying this to things, it better be a record of functions. But for now, let's assume I don't know anything else about the structure of this record, right? Maybe it's fixed by some other expression that I'm going to encounter later. So this is just something of type pi z. And then I've got two more arguments that I'm going to pass to whatever I select out of record D. I'll assume I know their type, right? So f is an A to B function, and x is a value of type Ka. K can be whatever type constructor you'd like, list, maybe, etc. Let's even assume that I know the result of this thing is supposed to be Kb. So you probably have a pretty good idea of what D is by now, but here we go. So now what I'm going to learn from this when I do type inference is that D, this record, should contain a field K with the type A to B, that's F, to Ka, that's X to Kb, okay? Writing this down formally, I would get something like this. I'd say the structure of this record, call that Z, had better have a substructure K labeling A to B to Ka to Kb. Okay, don't read this less than or equal to thing as having anything to do with subtyping or anything like this. This is a domain-specific constraint. It's just about record structure, right? Now, the problem that I have is that D doesn't actually have such a field. Instead, D's K field is actually of type for all T in U, T to U to KT to KU, right? Capturing that formally, I'll instantiate Z here with the structure K labeling for all T in U, T to U to KT to KU. Now, when I'm trying to solve this constraint, I'm going to say, oh, great, both of these structures contain a K field, so their types had better line up. So let's try to line up their types. I'm going to try to unify the desired type A to B to Ka to Kb with the actual type for all TU, etc. And unification is going to fail because I have an arrow on the top at the left and a quantifier on the top at the right. So type checking here fails. And now I'm sad. So what did I want to happen, right? Well, what I wanted to have happen was to add implicit type arguments after D, right? If I'd known that cell KD was going to be polymorphic, I could have thrown in these implicit arguments A and B, instantiating that quantifier for all TU, and then I would have been happy. The problem is I don't know that cell KD will have polymorphic type in advance, right? If you remember the type of cell K, it's just at any type T, right? There's no hint as to what the structure of that type T is. And I said I don't know the type of D yet. It's just an arbitrary record structure Z. So at the time that I first encounter this, I don't know there's any polymorphism here, so I don't know to insert the implicit arguments. So the motivating question for this work was to say, how can I delay implicit argument insertion until I learn more about unknown types? Okay? So here's my answer, and I've kind of hinted at this already, right? If I discovered the problem during unification, then clearly the solution should be found during unification as well. So what I'm going to do is try to figure out implicit instantiations during unification. A brief side note, there are sort of two parts of the implicit polymorphism problem. One is implicit arguments, and the other is implicit abstractions, implicit lambdas. And I'm focusing entirely on the first problem, right? Implicit argument insertion. So I'm going to try to figure that out during unification, okay? So this is all part of a constraint generating type inference and elaboration algorithm. I take a term, I try to elaborate that to a term in which all the implicits are made explicit, all of the missing parts are filled in, and along the way I generate a bunch of constraints under which that elaborated term will be valid. Okay? I'm going to sort of eagerly solve those constraints when I can, but conceptually I have two different processes here which are interleaved. When I'm elaborating a term, I'm going to note all the places that I could later instantiate without necessarily knowing what those instantiations are. Those will then turn up in the constraints so that when I'm solving the resulting constraints, I'll discover where instantiation actually does happen. Okay? That's pretty high level. Let me try to elaborate. In particular, let me try to elaborate this term here. So I need to start out by noting where instantiation could happen. The intuition here is that instantiation can happen at any elimination form, right? Elimination forms always have a sort of arbitrary type in the conclusion, and so that's someplace where there could have been instantiation. I'm going to cheat by the way and consider variables to be an elimination form. So here are all the places where instantiation could happen in this term. There are 4 of them because there's 4 elimination forms. There's one of these which is of interest to this example though, and that's this form here, so that's where I'm going to focus the rest of this discussion. Okay? So what does it mean to note where instantiation could happen? Well, it means when I'm elaborating this term, I'm going to insert a potential instantiation here, right? That's this apparent type argument iota. The important thing is that, so iota here is a funny kind of metavariable. It doesn't stand in for a single type the way your normal metavariables would. This is a metavariable for a sequence of types, right? We could solve iota to a single type. We could solve iota to the empty sequence, in which case there's no instantiation here. We could solve iota to many type arguments if we wanted. These potential instantiations are also reflected in the type. So I'm still generating essentially the same information afterward. Z had better have a K field, because I'm selecting K out of it. And that K field had better be something that I can apply to an A to B argument and a K to A argument to get a KB result. None of that has changed, right? That was all right when I did type inference the first time around. The only difference is now I've noted, hey, we could do some instantiation first, right? So that's what this brackets iota here is. So think of this as a type former for potential instantiation. In the paper, I call this a pseudotype because it doesn't really follow the rules of normal types. It doesn't have introduction forms, it doesn't have elimination forms, and it's not going to be present after type inference. Right? This is solely a type inference time annotation of something that I need to figure out. It's kind of like ordinary metavariables. This type as a whole now, right, brackets iota blah, means any type that could instantiate to A to B to KA to KB. So that could just be like A to B to KA to KB directly, then I wouldn't need to do any instantiation. Obviously, it could be the thing that I want it to be, right, for all TU, et cetera. But it could also be for all AA, right? That's also something that I could instantiate to this intended type. Now, I've generated this constraint, and I'm going to go on with my elaboration process. But at some point, I'll come back and decide to solve this constraint, probably after I've learned something about Z. So let's learn something about Z. Now I'm going to start solving this constraint. So as before, I'll notice both of my structures have K labels, so I'd better make the 2 types line up. So I need to unify for all, or iota, brackets iota A to B to K to KB with the quantified type. Now before I had an arrow at the top on the left and a quantifier at the top on the right, so unification failed. But here I have a potential instantiation on the head on the left and a quantifier at the head on the right, so I have something I can do, right? Let's solve iota, and I'm trying to instantiate 2 quantifiers, so let's solve iota to both of them. Iota now points to the sequence of types, alpha 1, alpha 2, and I can instantiate that quantified type with these 2 new type variables, alpha, or metavariables, alpha 1 and alpha 2. Now the rest of this is standard unification. I continue and I'll solve alpha 1 to A and alpha 2 to B. So this is the information I'll end up learning. And now when I substitute back into my original term, we'll get cell KD, arguments A, B, and then F and X as I wanted. Okay? Now, you remember at the beginning I said every elimination form is an opportunity for instantiation, so we would actually have a bunch more instantiation variables to be solved here. And they're all solved by the same process. IOTA 1 is essentially going to capture the Hindley-Milner-esque, like, let's instantiate polymorphic functions at their, or polymorphic variables at their uses. IOTA 2 and IOTA 3, in this case, we're going to discover there's just no need for instantiation there. And so we'll get solutions that look something like this. But there's nothing really novel about generating these solutions. Okay, so that's the basic idea that I set out to implement. And this should seem far too simple to you, right? Like, there's no way this is actually the story. And that's right. I've left out the interesting part. There's no way that's actually the story. The problem is that sometimes the constraints I generate aren't quite so clear. So let's take what ought to be a simple example. Here's the identity function applied to the empty list. Okay? And there's nothing funny going on in the types here. The identity function indeed has type for all t to t, and the empty list indeed has type for all t list of t. So clearly, ID applied to nil should have type for all t list of t, right? The problem is there are two different non-trivial ways I can accomplish that in my elaborated language. So the easy way would be to just instantiate ID with the polymorphic type of nil for all t list of t, and then I can apply ID directly to nil, and I get back something of type for all t list of t like you expect. The slightly less obvious thing that I could do is to start out by instantiating nil to something. I've left out insertion and generalization of metavariables here, but we'll start out by instantiating nil with something, call it u. ID can now be used at a monotype, list u, and now at the end I can generalize over u again. So notice this isn't quite the boring eta expansion it looks like, because the type argument u has shifted into nil, right? If the type argument u were at the outside, it'd be a boring eta expansion. So I have two valid elaborations here. The question is, how does this show up in type inference, and how do I choose, right? So to see how this shows up in type inference, let's do a little bit of the elaboration of ID nil. Again, there's lots of potential points of instantiation here, but the interesting one is the instantiation of nil, right? So now when I'm type checking nil, I am trying to figure out the type of ID, the type of the argument to ID. I don't know anything about it yet, so it's some type variable alpha. And I know that alpha needs to equal, or some metavariable alpha, I know that alpha needs to equal the type of nil for all t list of t. But we'll notice that we could have done some instantiation of nil, right? So that's where this metavariable iota has turned up. Okay, so alpha is for all t list of t, but with the opportunity to have instantiated along the way. Now the problem with this unification constraint is that there are two possible ways I could solve it, right? I could either solve iota by the empty sequence, not do any instantiation, and then I can solve alpha with for all t list of t. I'm perfectly happy there. Or I could solve iota with, let's call it u, do a little bit of instantiation, and then alpha gets solved by list u. And these correspond to the two elaborations that I showed you. So when I first noticed this, I was real sad. I was like, man, I'm going to have to come up with some backtracking thing. I'm going to have to enumerate all the different possibilities, and it's going to be exponential. So I just did something stupid, right? The first thing I did was to defer these constraints as long as possible, right? I'm already generating and solving constraints. So if I generate some constraints, just look at them syntactically, they're ambiguous, I can kind of hope, right? Maybe that alpha shows up somewhere else, it's going to end up being fixed. Maybe iota shows up somewhere else, it's going to end up being fixed, and this problem will solve itself. If that doesn't happen, at the end of type inference, I start guessing, right? Now, there are multiple heuristics you could imagine here. I started being sort of a Hindley-Milner-esque type at heart by just saying, why don't I just try to instantiate as close to the variables as possible? Which basically amounts to saying always solve the outermost iota. And the cool thing is, for all the benchmarks that I found in the higher order polymorphism literature, these heuristics work. All right, they're clearly not general, they're clearly not complete, and I think there's sort of potentially a point coming back here of saying, like, here's sort of where the actual meat of this algorithm lies, but so far, do the dumb thing has worked out. So one of the reviews said, like, well, this seems like a really interesting idea, and it's a pity the authors didn't fully realize the possibilities of it. So I want to give you a couple of hints of what I think the additional possibilities of this work are. So one thing is, if you have an account for universals, it ought to dualize to give you an account for existentials. In fact, it does. It's very pleasant. I've implemented it. You can play with it in my implementation, and I'll write it up at some point. But I think that's not to me not the most interesting piece of future work. So let's talk about a term that I can't infer a type for. Okay, so here I have this function that takes another function f, applies it to 0, applies it to true, adds the result, and then I want to apply that to the constant function lambda x0. And I want to point out there are other systems, and you saw one this morning, which can perfectly happily infer a type for this. But they do that at sort of the cost of, I think it's a cost of, a significant expansion to the expressive power of the language, right? Where you make instantiation sort of a concept that programmers can reason about. For the moment, I'm sort of trying to tie one hand behind my back and say, what if we don't have instantiation constraints? How far can we go? So there are two interesting problems about this term. One is that I need to infer a polymorphic type for f. The other is that I need to figure out to generalize this constant function over here. Again, I'm not talking about lambda insertion, so I'm going to ignore the second part of that and just talk about the first part. The thing is, I think I can actually make some progress. I think it's kind of interesting what happens. So what happens when I try to elaborate this term? Well, I'll make up a type for f, call it alpha, and then I'll observe a couple of places where instantiation could happen. And the interesting ones are what I call iota 1 and iota 2 here, right? The two uses of f. I'm now going to extract some constraints for what I know here, right? I know that alpha had better be n to n because it needs to take the natural 0 and return a natural number to be added. But I had an opportunity to instantiate alpha along the way. That's iota 1. I also notice that alpha needs to be b to n because it needs to take the Boolean true and return a natural number. But I notice I could have instantiated I2 along the way as well. Now, right here, you can run this with my implementation, and it fails because neither of these equations by itself gives me enough information. Right? I'm going to look at these two equations, I'm going to say they're ambiguous, I'm going to wait until I'm done, I'm going to guess that one of them has the empty instantiation and everything will go wrong. But the point is, what if you tried to solve these equations simultaneously? It really seems like there's enough information here to solve the problem, and I think that's kind of a cool thing that this approach illuminates. All right, thank you for listening to the talk. There's an implementation of this, you can find it on GitHub. I'm also hiring a second postdoctoral researcher, so if you think this is interesting, come talk to me or shoot me an email, and I'm happy to take any questions.
Any questions from the audience?
So I'm wondering how much of this work depends on like a system like R omega, or can it generalize to things like dependent types or like theorem proving for implicit arguments?
I think it should generalize to arbitrary pi types. So yeah, so R omega is F omega plus stuff that doesn't matter. And so that means we have this nice stratification between terms and types. All the mechanism that I'm showing you should work fine. The challenge, I guess, would be the unification algorithm, right? Sort of as usual, and probably term synthesis. But other than that, it should be fine.
Hi, great talk. Just wanted to mention one of my usual useless observations, which is I think the simultaneous equations thing is a great question to ask. And I think if you look at some early work by someone whose name is escaping me, I'll tell you afterwards, you get the intuition that you might, when you look at simultaneous equations, you might want to think of them in terms of algebraic varieties, and that could be a lot of fun. So I'd love to talk to you about that afterwards.
Sure.
Okay, let's thank our speaker again. Okay, and while our next speaker is setting up, we have Willem Lippold talking to us about two different approaches to graded types.
Okay. Okay, here's what I'm hoping you will get out of this talk. So if you already work with graded type systems, I think this paper presents a new map of the tools we have available as language designers. And if you don't yet work with graded types, my hope is that, you will learn something and perhaps feel inspired to use them in your next type system design. Indeed, these ideas have are being adopted in programming languages. Examples are Hack with its capabilities, Idris and Agda with their quantitative types, Linear Haskell, and of course OxCaml with its moding, just to name a few. Now, what is this grading thing, you ask? Grading is, roughly speaking, a way to enrich types with algebraic structure, which reflects part of the program structure at the type level. And this then lets us reason in a more nuanced way. So modal types, sort of type constructors we have in our systems to help us distinguish certain pieces of data, they give us a binary analysis. So the good old monad is a very good example of this. We might use a monad traditionally to distinguish pure and impure data. So here on the left, we have a pure A, and on the right, we have an impure A, an M of A. So we have either pure or impure. Similarly, in linear logic, we have a bare A would be just a linear type, and bang of A, so that exclamation point, we call it bang, that's a type constructor signifying that this piece of data can be used arbitrarily. So how do we get from modal to graded modal? Well, we index our modality by some algebraic structure, which has some sort of relation to the underlying, to the carrier modality. So in the case of monads, we have the unit of the monad and we have the join, so we want some algebraic structure that reflects that. So Wadler and Thiemann showed that we can extend monads to so something that is equivalent to effect systems with a monoid. In their case, an effect set, yeah. And similarly, for linear types, we can generalize the bang of linear logic, that is binary. We can index that with a natural numbers semi-ring, and we get an upper bound on the usage of the variables instead of just a linear versus nonlinear analysis. So that's tried to make a pretty picture for you to show the spectrum that you gain with this technique. Also note that usually these things will be some sort of partial order. And here's the picture of what happens to bounded linear logic, or bounded linear types, as it were. So I said that we want to reflect program structure into the types. Let me just make that concrete with a few small examples in the Granule programming language. Granule has co-effects baked in. That's what it's all about. And by default, it's a linear language. And so if we want to drop some data, like in this example here, if we want to discard it, then we need to wrap the input under a modality, and we index this modality with a 0. That is the natural numbers semi-ring that says we're using this variable 0 times. If, on the other hand, we want to use the A non-linearly because we're going from A to pairs of A, or box of A to pairs of A, we get a 2 grade showing 2 usages. Okay, a somewhat more interesting example, but you don't need to understand the details, just to show you that this is a sort of graded function composition, and in the end, we get sort of a scaling of the constraints, and we have n times m on the output function. Don't worry about all the bits, just to get an idea. Basically, this is an overview of what is happening. The semi-ring structure sort of reflects what's happening at the level of the typing rules, and that captures aspects of data flow. Now, bounded linear logic, there were 3 research groups in 2014 that sort of independently noticed that you could generalize this analysis to sort of arbitrary semirings. There is no reason why we need to, stick to natural numbers. And this fit into this sort of co-effect idea that had been born just a year earlier in 2013. And this is one way of implementing co-effects. Now, what are co-effects? Someone actually just came up to me and asked me that. Here's the definition. So a co-effect dual to effects tracks the requirement of a program on its execution context. The prime example of which is linearity. There are other examples like security lattice in the literature, sidedness, capabilities, tonicity, sensitivity, etc. So after 2014, there is this flurry of literature. I'm not sure if you can see the left-hand side is meant to be sort of purple and the right-hand side is meant to be green. It looks pretty white from here, but so there is this flurry of literature that developed, and basically it can be sort of that came out of these three generalizations of bounded linear logic, and this question arose: is this stuff compatible? So are the linear-based systems just as expressive as the graded-based systems? Can we transfer results from one to the other? And that's the question that we're trying to solve in this paper, or trying to answer. So let me just quickly explain, when I say linear-based and graded-based, what am I talking about? So it's funny, it just looks kind of different up there, but oh well. So on the left, we have linear base, and in the types, we have a linear function, which often we write with a lollipop, just to say, hey, we're cool, we're doing linear types. And we have a graded modality for that, that could be a box or a bang, that's sort of just a syntax choice. And then assumptions, contexts are sort of stratified into linear assumptions and non-linear graded assumptions. On the other hand, on graded base, we have a graded function arrow. In linear Haskell speak, you would say perhaps linearity on the arrow. And contexts are always, the assumptions and context are always graded. So the main takeaway of the paper is that the expressivity of both systems is pretty much equal, which is cool. And this is the map that I was talking about earlier, that I promised you. In boldface, we have the different calculi that we studied, that we sort of came up with as representatives for certain parts of the literature and the practice of programming languages. Obviously, on the bottom right corner, we have IDRIS2. Obviously, that we don't have dependent types in the graded modal core. We're just trying to capture the aspects that are relating to co-effects for clarity. And so the arrows between these two sort of between the left-hand side and the right-hand side, those are translations which we study in the paper. Unfortunately, I don't have time to show you all of them, but we can look at two. So what is even linear base and graded base? So hang on. Okay, this is a bit rubbish, but I highlighted sort of parts which are different, but for some reason it's not translating to the screen. But, sorry? Okay. It's okay, we can live with this. So we have box introduction or promotion. That is sort of, so what I wanted to say, essentially, this is, beautiful, hey, thank you. All right, Technicolor. Oh, that's a bit much. Can we tone it down like halfway? Perfect, lovely. All right, still a bit Technicolor, but we're in America, so that's good. So we have box introduction, which is something different, additional syntax to lambda calculus. We have box elimination. Linear functions, that's just sort of a different symbol for the same thing. we have our graded modality, which we saw earlier, our graded assumption, which we also just saw. And then on the graded base side, also I think we just saw this, so we have graded function arrows and graded assumptions. Note, in graded base, there is no modality right now. So let's start trying to translate this. So contexts, graded base contexts to linear base, quite straightforward. There is only one type of assumption, and that sort of translates cleanly over. Bit more interesting thing is happening here in the types. The graded function arrow, the R-graded function space gets translated to a linear function space in linear base, where the right-hand side is under an R-graded modality. And then consequently, we have to box the right-hand side of an application and do an unboxing in the abstraction body to sort of make everything line up. And yeah, that's where sort of propagation of constraints happens. These are theorems we prove in the paper. Type preservation, just simple operational correspondence, and equation preservation. Now, translating linear base to graded base, we have two types of assumption that we need to translate differently. We have the linear assumption that we translate as a one-graded assumption in graded base. Now, we get into trouble trying to translate our modality. If you recall, there was no modality in graded base. This is all we have. So the only place I see an R is on the function space, so somehow we're going to have to use that. And it turns out, yes, well, after poking around quite a bit, if we do a CPS transform, we can sort of make it work. And then everything just, I mean, isn't that beautiful? It's not really, but yeah. I mean, it's beautiful conceptually, but maybe not to work with. And then consequently, also, of course, our theorems come out, slightly mutilated. No, I mean, fine, but we do require now full beta reduction in the target, and equation preservation now is up to function eta, but that's just sort of standard for Plotkin's call by name CPS transformation. Fine. Okay, but what does happen if we add a graded modality? Like, for example, this is very close to minus the dependent types, but what Chowdhury et al. Have in their 2021 paper. So we add the yellow bits to graded base, and now, ta-da, as expected, we sort of get a very clean translation between the systems. No huge surprises there. What if you don't have a box modality, but you have polymorphic types? Can you do better than this? Well, taking inspiration from Bernardi et al.'s work on linear Haskell, they have this unrestricted type constructor, and this was generalized by Hughes et al. To this sort of indexed version, which in Granule that would be a co-effect polymorphic, but in linear Haskell, it's that R would be a multiplicity. And if we do a sort of a church-encoded version of that, this is what we get, and details in the paper. Sorry, no time. But yeah, it's very nice because then you sort of don't need to do the CPS transform, and everything sort of plops up. Yep, so to sum up again, the main takeaway is that the expressivity of both systems is equal. Yay. Little asterisk. In the context of products and sums, interesting things happen, which you're going to have to read the paper to find out what. And it just says something about the difference in expressivity between these two different type systems. And yeah, enjoy.
We have time for a few questions, if there are any.
not everyone at once.
Okay, so actually I do have a question. So if you have these systems and they're now equivalent, as you proved, why should I reach for one over the other? Like, why is Idris 2 making the choice to live on the left-hand side
Yeah.
and so forth?
Oh, that's a great point. That's the slide I deleted. So if you go down the graded base route, you're probably going to have less verification effort as a language designer because you don't have stratified contexts to deal with. That's something we noticed, that the formalization of things is just easier. I think also in graded base is backwards compatible. Like, as linear Haskell shows, you can sort of add it to a system later. So my guess is probably that's the more convenient system, but
cool.
It's just sort of a feeling.
Hello, lovely talk. I have a rather basic question. I've just always been very confused about the difference between effects and co-effects. So I was wondering if you could give like an example of what some sort of like concrete linear co-effect thing would be. Would you be able to model like the opening of like a file this way, or?
Yes, absolutely. And there are actually things which can be modeled both as effects and co-effects. But there are things which can only be modeled as one or the other. And opening file handles is actually an example we have in the granular programming language. I'd be more than happy to show it to you.
Is it an example of both or one, or?
No, I mean, you need linearity. I think there is work of doing linearity related to monads. I'm not sure whether it's impossible to do, but in a sort of an effectful setting. But yeah, I'll have to think about that.
Okay, cool. Thank you.
Thanks.
Okay, let's thank Willem again. Our next speaker is Sergey Goncharov, and he's going to talk to us about higher order bialgebraic denotational semantics.
Yes, hello, indeed, this is me. And this is joint work with these wonderful people on the slide, Mark, Stelios, Henning, and Stefano, affiliated accordingly. So this is a work on categorical semantics, and I would like to say first that it's a part of a broader effort. It started like 3 years ago, and I tried to summarize it on a very high level on the slide. So the main idea is use the tool set of the category theory applied to operational semantics and sort of consider an operational semantics in terms of syntax and rules, and use a categorical abstraction as an intermediate level, and then using the categorical methods to obtain general methods useful for the semantics and general properties. Methods, I mean things which are important for reasoning about programs like logical relations or abstract house method and other things, and properties are like compositionality, program equivalence, contextual equivalence, adequacy, so all the things that are very difficult to prove on a case-by-case basis, but which we hope can be facilitated if we use category theory and prove general theorems, like if you have this and this assumptions, then this and this general result follows. And then, like, nice side effect of this is that since it's categorical, it often has, as a kind of a byproduct, some sort of formalization in type theory or in functional programming languages and proof assistance and so on. Right, so as I said, this is like a big framework which we're developing over time, and here in this talk I'm going to focus only on a very specific part. Well, the talk contains the word denotational semantics, and this is the new part. We contribute to this framework because we previously have been only working on the operational side, and the denotational side wasn't very clear. And this work is meant to like maybe not close this gap, but contribute closing this gap. So you know certainly that operational semantics is about execution of programs or program behavior. Denotation semantics is about what programs mean. And there are two important desiderata for denotational semantics. One is compositionality. So that semantics of a term is built from its parts, and the adequacy is a relation between dentational semantics, operational one. So if two denotations are equal, they must be behavioral equivalent. And so the questions that we are posing here and trying to answer is, can the dentational model be read off from the operational semantics rule? And can adequacy property, which again a very important property that like lots of instances being proven in lots of papers, can it be proven henceforth for such a definition? So here's a rough plan. Yeah, there are kind of quite a bit of introduction, quite a bit of scaffolding, because I need to introduce this context in which this facet that we're contributing is fitting. So I need to explain what is higher order abstract GSOS. And then I explain the notion of locally finite logical algebra. So this is a notion which is novel and which we contribute with this work. We explain how to construct them in the so-called M categories, and I briefly mention some further example and then conclude. So here's a little introduction about into higher order abstract GSOS. So GSOS is a certain format of rules of operational semantics. So it basically says, well, what is allowed? It's a certain restriction, but it's quite general. And why it's important in this context is because there is a seminal work by Ture and Plotkin in 1997 who found that actually this exact format is very category theory friendly. So there is a very nice categorical abstraction of that very format, and the parameters of their framework are exactly a signature in the functor, so the syntax of your language, behavior in the functor, so like the structure of the transitions, and the so-called GSOS law, which is an abstraction of the rules. So if you have got a system of rules that determine the operational semantics, you have a generic procedure to obtain this natural transformation with which you can then work categorically. And here's a quick example, a very primitive one. Was from process algebra. So basically, if you want to see where sigma is, sigma are the operations that occur in the rules, and behavior are the transition signs. So they can be labeled, unlabeled, or they can be multi-array or something more complicated. And yeah, roughly they correspond to these occurrences in the GSOS law. Right. So so why it's so cool, the result of Plotkin, Ture and Plotkin, is because they introduced, so now with these premises, they introduce a certain categorical machinery. So they introduced a category of row algebras, which are jointly algebra and algebraic and algebraic structure plus a certain coherence condition called a bialgebraic law. And it has several implications. So in this category, we can consider the algebra of terms as an initial object. This follows it. The algebra of terms promotes to an initial object, and the final coalgebra of the behavior functor promotes to the terminal object. And then, if you know the very basics of category theory, in a category with initial object and the final object, there is a universal arrow from the initial one to the final one. And this, magically, this arrow is the semantics. So you have this arrow in the middle of this picture from the algebra of terms to the algebra of behaviors. And by the universal properties of this framework, so you get compositionality of the semantics for free and the adequacy result. So it's very cool and very satisfying mathematically. One of the issues with this formalization is, so it's very general and therefore it's very restrictive. And one restriction is that it didn't handle higher order languages. And this is where we jumped in with a generalization called higher order GSOS. So we modified the framework essentially in exactly two places. So we maintain the signature functor as it was, but the behavior functor is now a mixed variance functor. Why? Because our transitions are now programs like lambda terms, and they can not only reduce, but they can take over arguments on which the programs evaluate. This is what makes the language high order. And this corresponds to this slot, the first slot of the behavioral functor, which is now contravariant. So now you need to modify the GSOS law accordingly. It goes through. So you need to additionally say that it's denatural in X. I will not explain what is that, but it's some version of naturality. What is naturality? I will also not explain. But it's a sort of polymorphism mathematically. And here's one example, is one of my favorite examples, because it makes it very easy to illustrate it. So actually I have two favorite examples. One is combinatorial logic and one is typed combinatorial logic. So this is a typed version. So, and X stands for extended because it's not the textbook combinatorial logic. Because we need to modify it slightly, very harmlessly, in order to fit into DSS format. So we need to have two types of transitions, so labeled and unlabeled. And labeled ones are exactly the ones where so the unlabeled correspond to beta reduction, and the labeled one is like applying your program to the label. So it's kind of, we refined the standard semantics, but it works exactly the same way. Right, we also, for this reason, we need this auxiliary multi-array combinators, because if you, for example, start evaluating the constant combinator, then if you feed just one argument, then it just turns it to something, and if you apply another argument to that something, that will produce the first argument. So you need to record this intermediate programs. So here is this behavioral functor which we obtained from it. And so intuitively, what is this? So we interpret this functor in multi-sorted sets. So because we are typed, so the carriers of our language, of our term algebra, they are indexed by sorts. So here, for example, I have got the unit type. So what is the behavior of unit type? That's carried by the sort of the next term, or it's +1, meaning that we are so there is no beta reduction. So we just finish. And this +1 indicates that we stop. And if we apply this functor to the function space, then this disjoint sum, it corresponds exactly to the case of beta reduction. So it's indexed exactly by the same type as originally. Or to the case when we evaluate, and then here we've got functions from X to the T1, which is the carrier of terms typed with T1 to the carrier of terms typed by T2. So I'm detailing this precisely because I want to indicate that on the right-hand side, the indexes of Y, the biggest index, is the same as on the left, T1 to T2. But the index at X is T1, which is properly smaller. So this will play a role later. So here, perhaps I will skip this. So this is the way how the rule correspond to this natural transformation. So this perhaps requires some time to see how I color-coded this. But yeah, it takes some time to grasp this. And just like Turing-Plotkin originally, we can introduce higher order bialgebras. And we can modify the notion of row bialgebra. And again, it's still true that the algebra of terms promotes to the initial object. And you think, okay, now if we generalize the second part, the notational one, then we can completely repeat the success of this story, this nice diagram. But the point is, final bialgebras need not exist. There is like a bit of a technical argument, which is in the paper, I cannot reproduce. But I mean, it cannot be as easy in higher order languages. Otherwise, higher order languages would be very simple if this just went through. And so still we can define notion of program equivalence, which is so-called strong applicative bisimilarity, as a strong version of Abramsky weak applicative bisimilarity, and compositionality of behavior equivalence goes through. But, so there is no, we can stay on the operational side, but what is the notational side? This is like an abstraction here. And yeah, so here, I just briefly explain what's the problem. So the problem is that essentially what we want is to compute fixed points of functors. And when we compute fixed point of the signature functor, we get all terms. Because we start with empty set, then we apply sigma to it, we get all constants, then we apply it once again, and then we get terms of rank 1 and so on, and in the limit we get all terms. And for the final coalgebra, we go all backwards, and it still works for covariant functors. But for mixed variant functions, it doesn't work because there are two parameters, and we're sort of shrinking along one parameter and expanding along the other parameter. So what our contribution is, one of the contribution is this notion of locally final coalgebra, which actually is like this. So it's very impredicative. It says, a locally finite coalgebra Z is such a coalgebra that if you fill the first argument with it, then the result is the final coalgebra. So it's not clear at all why such a thing exists, and it's one of our contribution why it does and how it's constructed. So here is an example for XCT. Before I proceed with this construction, so one thing which follows is that every row by algebra is adequate. So if you can construct at least one locally finite coalgebra, then you can always get automatically an adequacy result for it. And you can get compositionality under this additional assumption, relative flatness, which I also don't have time to explain. Right, so let me just quickly sketch how the locally finite coalgebra is constructed. And this doesn't necessarily work in any category, but if you work in a so-called M category, these categories are enriched over complete ultrametric spaces, then they can be more or less always constructed once your behavioral functor is locally contractive in the first argument and locally non-expansive in the second argument. And this is actually the case for the XTCL functor, because you can define metric in such a way by measuring the discrepancy of functions on types. So it's like if they diverge, well, if they differ on larger types, then the difference between is smaller. So if you visited today's beautiful lecture by Edward Lee, so he was using exactly this metric. And here it's kind of repurposed, but the construction behind here is again like a Banach fixed point theorem through this metric, which is an abstraction of induction over types. Yeah, so there are a number of examples. Don't have time to go through them. So you can play more with multi-sorted sets. But all this framework is also instantiated beautifully in the topos of trees. So you can work with untyped languages and use this guardedness triangle, if you're familiar, to work with other languages. Right, so we introduced this new notion of locally final coalgebra, which filling the gap of finding a canonical denotational domain for categorical operational semantics and prove the theorems. Yeah, so there are lots of further work, in particular generalizing from strong bisimulation to weak bisimulation and considering order-enriched categories instead of the metric-enriched ones. Thank you.
Okay. Do we have time for one question as the next speaker is starting to set up? Max?
Okay, thank you for the talk. This all seems backwards to me, which is that I would like to come up with a denotational semantics, and then I would derive an operational semantics, right? That's what I would normally do. So my question is, for languages like this one where we have existing denotational semantics, does your method reproduce these existing denotational semantics? Or is it related to those semantics we already know?
Well, if we talk about topos of trees, then I would say yes. I mean, we obtain the semantics that is used there. So with
so you reproduce the same semantics.
It remains in this talk. It remains intentional. So it's not going to be a domain theoretic semantics. Yeah. But if we agree that intentional semantics is also can be called denotational, then this is kind of where it's fitting.
Cool. Great. Thanks.
Awesome. Okay, our next speaker is Maria Nicoleta Cracciun, talking to us about infinite dimensional probabilistic programs.
Yeah, hi, I'm Maria, and I will talk about how to adapt Hamiltonian Monte Carlo for lazy infinite dimensional probabilistic programs. This is a joint work with Lu Kong, Tom Schreibers, and Sam Staten. So probabilistic programming treats statistical modeling declaratively, so the user writes the prior... sorry. Is this better? Now? Oh, okay, great. Okay, so the user usually wants to write the prior and the likelihood as a high-level program, and then a generic inference engine will give us the samples that come from the posterior. So, for example, in Haskell, using laziness, we can express stochastic processes and other non-parametric Bayesian models. And these models are over implicitly infinite dimensional spaces. So the number of parameters is unknown or unbounded. And designing general purpose inference algorithms that work well for this kind of models is quite challenging. Hamiltonian Monte Carlo is one method that is very successful, and it sits at the base of Stan. However, it was built to only work for finite fixed dimensions. So in order to combine these two, we'll have two problems that arise from this. So the first problem is that the HMC requires the gradient of the likelihood to propose the next sample. And in our setting, this is going to be infinite dimensional. And when proposing the next sample, HMC accepts it according to the acceptance ratio, which traditionally includes one factor per dimension. And this will result in some infinite products. So to address the first problem, we introduce a smoothness condition called packup, and we will define this a bit later. And under this condition, at almost every point, the likelihood only depends on finitely many coordinates. So in other words, the gradient is finitely supported. And we proved that every program in our core calculus satisfied this. And we use sparse map Nagata numbers AD to get the support of the gradient together with the values there. And to address the problem of the infinite products in the acceptance ratio, we designed modified HMC integrators such that the contribution of all but finitely many dimensions cancel out in the acceptance ratio. Hence, we'll get a ratio that consists of finite products. And we built several lazy HMC variants with this cancellation property, including a lazy nuts version, which comes from the no U-turn sampler. So why do we care about infinite dimensional models? Well, this is basically what it's called Bayesian non-parametric modeling. And take, for example, the clustering model, in which we have some data points and we want to group them, but we don't want to fix the number of clusters in advance. And instead, we want to infer it. So the number of parameters is unknown. The same happens with stochastic processes, such as random walk or change point process. They have no a priori bound on how far they run. And in all these cases, the parameter space is unbounded and implicitly infinitely dimensional. One way of dealing with this type of models is to truncate them, but this would only give an approximation, and it is not compositional. So the seed in our setting comes from a probability space omega together with a measure-preserving isomorphism that so that the source of randomness can always be split into two, which is exactly what monadic bind uses. This idea comes from the lazy people library. So the implementation uses a rose tree, which is an infinitely wide and infinitely deep tree with an independent standard normal seed at every node. Formally, it's just a function from a set of addresses to reals, and in our case, the set of addresses is infinite dimensional. So the whole tree is the state of the Markov chain that we want to move around, and for simplicity in this talk, we will use a stream of seeds. So at any run, the likelihood needs only finitely many seeds. If the seed of a site has been used in the computation of the likelihood, we say that the site was visited, and we can also distinguish between sites which have gradient 0 and gradient no 0. We say a site is not visited if it is not touched during the computation of the likelihood, and different runs can have different visited and not visited sites. So the key language idea comes from the lazy people library, and in the prob monad, we can write IIDP as an infinite list of independent draws from the probability distribution P. And this means exactly what we write in statistics, which is to have a sequence of independently identically distributed random variables. So we can write the geometric distribution as first taking an infinite sequence of coin flips and then returning the index of the first success. And when we run this, evaluation demands the first flip, and then only as many more as find index actually needs. And when we get the first success, evaluation stops, and then the rest of the infinite list is never actually built. So the number of sites in this program that the program touches is random, and in fact it is the return value of the program, so we can't really fix the dimension in advance. So that's the expressiveness that we want to keep, but again, performance correct inference is challenging. So consider the following model, which is a piecewise constant regression. We have 6 data points, and we want to fit a step function on them. The prior for the change points comes from a Poisson process, and the heights are normal draws. Notice that the splice combinator samples this into a random function. Then the model scores each data point under Gaussian noise around f of x. So a draw of f really has infinitely many segments. However, only the segments that are actually demanded by rendering the figure or by the likelihood are actually built. The smoothness condition packup stands for piecewise analytic under cylindrical analytic partition. So remember that the seed space is infinitely dimensional, so it's R to the set of site addresses, and we want to split the seed space into countably many pieces, one for every way the control flow can go. On each piece, the likelihood is an analytic function of just the finitely many seeds it reads there. So for example, on U1, L depends only on the second and the fifth seed, and changing any of the other seeds doesn't change the output of L. And we want the pieces to be cut out by analytic inequalities, so the boundaries of the pieces have measure 0, and then we'd never actually land on them. So then if L is packup, we know that the gradient of the likelihood exists, and it is finitely supported. And this is exactly what we want. Here is an example of a function which is not packup, and that is because it depends on every dimension and not finitely computable. Our core calculus has reals, finite products, and countable sum types, and the constants are piecewise analytic primitives. And the typing rules are standard, and we also get primitive recursion over naturals and stream co-recursion. We can also express the lazy people monad in the calculus, so then the likelihood is also expressible. We prove that such likelihoods are packup. And again, this means that they only depend on finitely many inputs locally, and the gradient is finitely supported. It's worth mentioning that programs with unbounded search, such as the find index in geometric model, are not inside our calculus, but we can verify backup directly for those. So how do we actually compute the gradient in practice? If we were to use an naive 4-mode AD, then we would need infinitely many passes, as we would need 1 pass per dimension. So instead, we adapt the idea of Nagata numbers with a sparse map tangent to the infinite dimensional settings. So in 1 pass, we get the value and the whole gradient as a finite map. And in Haskell, this is a floating instance, and using laziness, we make sure that we only touch the dimensions that we actually care about. In finitely many dimensions, this would be an optimization, but here it is essential because we need to get the sites which have non-zero gradient. So, and this is exactly what we get from the AD. Notice that there can also be sites which are visited but have gradient 0. So for example, in the step regression model, we have sites E1 and E2, which corresponds to the change points. They have gradient 0 because locally the likelihood depends only on the height of the segments. So let's have a quick HMC recap. The goal is to sample from a distribution. We only know up to a normalizing constant. And we can picture the negative log density as a frictionless landscape, so downhill is more probable. And if we put a pack on the surface and we let it slide into the valleys, then we would get some optimization, but we also want to sample from the sides and from the other valleys in the right proportions. So at every iteration, HMC gives the pack a random momentum kick and lets it glide for a while. And we can record the position at where it ends up being, and we can propose that position. The system follows Hamiltonian dynamics, so the total energy is the sum of the potential and the kinetic energy. And we end up sampling from this joint distribution, but since the momentum and the position are independent, then we can just throw away the momenta at the end. To get the position and the momentum after some time t, we will need to solve some differential equations. This in practice usually is not possible, so we use a numerical integrator, and we basically approximate the equations by discretizing time. One of the most common such integrators is the leapfrog integrator, which does L steps of size epsilon, and epsilon and L needs to be user specified. So one step of the leapfrog integrator looks like this. We first do half of momentum kick, and then a position drift, and another half of momentum kick. So notice that we need here the gradient of the potential energy, which contains the gradient of the likelihood. So if you write the target density as the likelihood times the prior, which in our setting is the standard normal distribution, one iteration of the HMC looks like this. We first sample the momentum, and then we apply the leapfrog integrator to the position and the momentum, and we get a proposed position, Q prime. So to account for the approximation error introduced by the integrator, we have to include an accept-reject state. So two things to remember is that HMC needs the gradient of the likelihood, and we deal with this by ensuring pack-upness, and then the acceptance ratio has 1 factor per dimension, as we saw. We prove correctness for our methods by showing invariance, so one iteration of the sampler must leave the target distribution unchanged. And we start from the involutive MCMC framework, which has as a proposal an involution, which is a function which is equal to its inverse. And in our case, the involution is the leapfrog steps and the momentum flip at the end. And then the ratio has to account for the change of measure of the involution. And at each site, we draw from a normal distribution independently, but the samples are actually drawn only when they're needed. So informally, we can view the acceptance ratio as this ratio of infinite products, and what we want is that for all but finitely many sites, the ratio, so what we want is for the update, so the involution, to preserve the joint density for all but finitely many sites. And if this happens, then the ratio can be reduced to a ratio of finite products over indexed by a finite set S. So we use modified HMC integrators with the following property. If at a site I, the gradient of the likelihood is 0 for all the positions in the HMC trajectory, then the update preserves the joint density. So the finite set of sites S that need to be included in the acceptance ratio consists of all the non-zero gradient sites along the trajectory, which we can get from the sparse map Nagata numbers AD. So this also solves our second problem. We have two variants which have this property. The second one uses different Hamiltonian splitting than the usual one. And we can also use the original leapfrog integrator for the visited sites. And however, we need to be more careful there and use a density preserving update for the other sites. And we need to inspect Haskell tanks in order to get all the visited sites, since AD only gives us the sites with non-zero gradient. And we also have a lazy version of the Neuwirth sampler, which is the default sampler in Stan, and adaptively sets the trajectory length. So there is no need for the user to specify the number of leapfrog steps. Looking back at the step regression model, we can see that the second segment is not a great fit for the last data point. And even though the gradient at E1 and E2 is 0, the prior and the momentum can still change the values of those. So if the second change point, moves to the left of the last data point, then another segment needs to be built. And hence two more seeds, which are going to be C3 and E3, are going to be visited. And now the gradient information from the likelihood can guide the third segment to better fit the last data point. So this is what multiple draws using our first HMC variant looks like. And we also tested our methods on other non-parametric models, such as polynomial regression, with the degree being unknown, random walk model, infinite Gaussian mixture model. So to summarize, we have addressed two problems. First, HMC needs the gradient of the likelihood, and PACAP guarantees that for the gradient is finitely supported, with sparse lazy AD discovering exactly those sites. And the acceptance ratio looks like an infinite product, but with the right integrator, the contribution of the zero gradient dimensions cancel out. And then the product collapses to a finite one. So together, that means that laziness keeps non-parametric models compositional and declarative, and lazy HMC makes gradient-based inference possible on such models. The code can be found on GitHub as an extension of lazy people. Thank you.
Okay, we have time for one or two questions. If there's any from the audience, I actually have one. Let's wait to see. No. So last time I played with HMC-related inference, it was in the context of generators and distributions there, but I had there was a lot of need for manual tuning of things to make things work. And you didn't really touch upon that at all. Did you find that to be a problem? Is that somehow not a problem in this context?
It is still a problem in this context.
It's still a problem. Okay,
yes.
Good.
That's why we want to also try to make nuts work. Oh, sorry. So yeah, it is still a problem, the tuning of the parameters. That's why we want to make nuts work as well. And nuts also has some adaptive step size epsilon that we didn't take into consideration yet, but this is a future work for us. So yeah.
Thank you. Let's thank our speaker again. And our last talk for the session and for the day is Jack Leal talking to us about imprecise probabilistic programming.
Precisely. Okay, yeah, I'm here to talk about imprecise probabilistic programming, precisely. So this is joint work between myself and Sam Staton from the University of Oxford. So yeah, I'm aware this is the last talk of the day, so I'll just launch into it. So yeah, in order to, we're working with imprecise probability. So what is that? So before we get there, let's just ground ourselves in what probability is. So one way to think of it is a probability is just a point in the simplex over the output space. So here, if we have 3 possible outputs, red, green, and blue, the simplex is a triangle. And we can think of a point in this triangle as representing a distribution over these outputs. So at each of the vertices, this represents certainty of that point happening. The point halfway between green and blue on the line would represent equal odds between green and blue. And this point P here would represent, higher chance of green happening, but, red and blue are still both possible. So this is one-to-one with any distribution over these 3 points. But Ellsberg came up with a kind of thought experiment, which he said, okay, what happens if I have an urn which contains 30 red balls and then 60 balls which are either green or blue, but we don't know the bias? He asked people what they would bet on based on this urn, and it turns out people prefer to bet on the outcome of red rather than green. And there's no single probability which can justify this preference. So this is why we move to imprecise probabilities. What an imprecise probability is rather than a single point, it's a convex set of distributions, which we call a creedal set. So this encodes something called Knightian uncertainty, where basically none of these points are privileged across the others. Any point could be possible, we just don't know which one it is because we have an incomplete information about our world model. So for the Ellsberg example, the creedal set for the urn is basically a line segment, which is along the line where probability of red is 1/3 and probability of green and blue are the rest of the supporting mass, anywhere between 0 and 2/3. And so when we perform inference on imprecise probabilities, we're no longer looking at expectations and probabilities, we really care about minimum and maximum expectations or minimum and maximum probabilities. So in this talk, it's based off another paper me and Sam wrote, 2025 in Popple, which kind of built out the theory of imprecise probability as a monad because previous literature hadn't been able to capture a monad for imprecise probability that has all the properties you would want in the semantics of a probabilistic programming language. But in this talk, what we did is we embedded this graded monad into a Haskell DSL so that we can perform inference on it in many possible ways. So we used type level names based on Lev's paper in order to track the Knightian uncertainty, which we showed was critical in the theory paper. We have imprecise, so what we showed, the core idea, is that imprecise inference actually needs no new extra compilation structure on top of what regular probabilistic programs use. And we have, just from one compilation strategy, we get actually 4 different types of inference methods based on how you instantiate it in order to probe the imprecise program in different ways. It's a very small package. It's only about 1,000 lines of code. And you can now find it on Hackage at this link, and the implementation is here. Okay, so to give an overview of the DSL, we can see that basically it revolves around the type imp G of A. So this is basically an imprecise output, which the result is of type A, and G is a type-level list of names which track the Knightian choices we make along the way. So we can code the Ellsberg example as an imprecise probabilistic program in our language, on the left here. And what we first notice is that we actually have a qualified do, because the monad we're working with is not a regular Haskell monad, it is a graded monad. And so we need to tell Haskell to desugar this into our monad, our monad bind and return, rather than what Haskell does regularly. And this allows us to talk about these imprecise probabilities in an ergonomic way. So we can see in the example that first we flip a coin biased to 1/3 in order to select whether the urn is red. And then we make a Knightian choice, so a coin of unknown bias, in order to choose between green and blue. And so when we ask for the interval probability that the Ellsberg urn is green, we get this, interval between 0 and 2/3. So semantically, this turns out to be a graded monad, which is down the bottom here. So this is all explored in the Popple paper. And the way to think about it is for each, we get a distribution for each Knightian valuation. So for each Knightian coin flip, which each way it's resolved, we get a different distribution. The names are, I guess the names are used to enforce commutativity of the program, which we'll get to later, but they're erased at runtime, so they incur no additional cost on inference. So to go into what the names actually do, why they're actually involved, we have two programs here which are almost identical, except in one program, the name is switched out for another name. So the first program, basically we flip a fair coin, and based on that, we make a choice. We flip a Knightian coin, and then choose either red-green or red-blue. So this first program, we flip a Knightian coin with the same name. And if they have the same name, it means that they have to resolve to the same bias, even though we don't know what the bias is. So in this case, if the Knightian coin ends up being certainty of true, then it doesn't matter what the fair coin resolved to, we get certainty of red, because this happens on the first if statement in both branches. On the other hand, if it resolves to certainty of false, then based on the fair flip coin, we'll get equal chance between green and blue. So we get the line segment from certainty of red to equal odds between green and blue. On the other hand, if we use a different name for the Knightian coin, so now A2 in the second branch, these two Knightian coins don't need to resolve to the same bias. So if the first coin resolves to certainty of true and the second coin resolves to certainty of false, then we can get the outcome, the program could have the distribution of equal odds between red and blue, which was not possible in the first program because both coins resolve to the same bias. So we end up getting a larger creedal set, as shown on the right here, because equal odds between red and blue are possible. Because the names are no longer dependent on each other, we get more possible distributions. So the reason we have names in the first place is they restore something called commutativity of programs. And this is something that's critical in probabilistic programming languages. So the point of commutativity is to say, okay, if we have two probabilistic processes, A and B, flip one coin and then another coin, and they're independent of each other, it shouldn't matter if we flip the first coin and then the second coin, or the second coin and the first coin, and then witness them, because, these things are independent processes. So the standard monad, in order to model creedal sets, the convex power set monad, actually breaks this law, because it does not track the dependency of the Knightian choices throughout the program. And so if we reorder programs, this is actually unsound. So we restored commutativity of the program by tracking the Knightian names, by tracking which Knightian choices occur, and we show that when the Knightian names are disjoint, commutativity is restored. So when actually programming with our language, in order to enforce that we don't have spurious correlations between subprograms with the same name, we enforce that the names are disjoint during the bind, and you can always explicitly ask for independence by just using a tag keyword. Okay, so now that we have what the DSL actually looks like, I'll show you how we actually the inference pipeline. So we use a standard trick in discrete probabilistic programs where we first use something called knowledge compilation, because the abstract syntax tree of our program is quite complex. It's hard to actually perform inference over. So we compile it into an easier object to perform inference. And here we use binary decision diagrams, which is just basically a canonical representation of a Boolean formula to guard each output. An example is on the right, where we have an if statement over 3 variables. And the way to figure out what's happening is first we look at each variable, and if it's true, we follow the solid branch. If it's false, we follow the dotted branch. And then, we follow this all the way down until we get a true or false statement. And so, this is a canonical and unique representation for each Boolean function. And this is what happens in other precise probabilistic programs like DICE. So this knowledge compilation happens by structural recursion over the abstract syntax tree. So when we come across a flip variable, basically we create a fresh weighted BDD variable with the weight given by the coin bias. But if we come across a Knightian keyword, what we do is we create a fresh unweighted BDD variable. But the point is, if we come across a Knightian coin flip with the same name, then we point that to the same variable. And this is how we enforce the variables to resolve to the same biases. So that's kind of like the insight we had in order to have this compilation pipeline. A Knightian coin flip is just the same thing as a BDD variable. It's just left with weight free until inference. So we can see how this actually affects knowledge compilation from the two programs we saw before. These two BDDs are the guards for the outcome of red. So in the dependent program, because the two Knightian choices have the same name, it turns out that X becomes a redundant variable flip, and the binary decision diagram reduces to just a single test on A1, which will give us false if A1 is false for red, and true if A1 is true. For the independent program, because we have independent 19 names, all of these variables contribute to whether red ends up being true or false, so we get this more complex binary decision diagram here. So yeah, they end up being separate, and we end up getting this wider, this decision diagram which represents this wider creedal set. Okay, so now that we have actually compiled our program down to something which is quick to perform inference over, how do we actually perform inference? Well, we use an algorithm called WMC, weighted model counting, which is also very standard in discrete probabilistic programming literature. And the point is that the WMC algorithm is defined inductively over the binary decision diagram. So if we're at a true or false leaf, we just give it 1 or 0. But if we're at a variable, we perform it inductively over each node, one for the false branch, one for the true branch, and then we multiply this by the weight of the variable. So for a probability, this would be 1 minus p for false and p for true, and then we combine that all together. But what Kimmig et al. Noticed is that this is just only using the operations of a semi-ring, 0, 1, plus, and times. So what we can do is during inference is instantiate our WMC algorithm over different semi-rings in order to probe our imprecise probabilistic programs different ways. So if we just use the standard real semi-ring, where we instantiate probabilistic weights to p and 19 weights to all combinations of 0 and 1, we can perform a WMC pass for all of these combinations to get the exact bounds and minimize or maximize over them, but this is of course exponential in the number of 19 values. On the other hand, we can actually use gradient semi-ring, so this has that raw number as well as the gradients of the derivatives with respect to each of the 19 variables. So when we perform one WMC pass, not only do we get the distribution, but we get the gradient as how the gradient is affected with respect to the 19 variables, and so we can actually perform gradient ascent or descent over the creedal set in order to optimize the probabilities. Another one is symbolic. This is actually not in the paper, but reviewer 4, thanks to whoever that was, pointed this out as another semi-ring we could instantiate to, is to use a symbolic semi-ring, so a multinomial representation of the creedal set by instantiating the probabilistic weights as constants p and the 19 weights to a unique variable. And then with one pass of the WMC algorithm, we get a multinomial representation of the creedal set, and then what we can do is some kind of corner search or branch and bound algorithm in order to find the minimum and maximum probabilities of this new object. Finally, we can use an interval semi-ring. So probabilistic weights get instantiated to the point interval, whereas 19 weights get instantiated to the full interval between 0 and 1, true and false. And then we'll get interval bounds in just a single pass, so super fast, but then we run into the dependency problem of interval arithmetic, where we have the high weight and the low weight of the 19 variables are both the intervals between 0 and 1. So there's no way to enforce in the algorithm that the low weight should always be 1 minus the high weight. And so we kind of have this decoupling as the algorithm propagates. And so while the bounds are still sound, they're not necessarily tight. So we might over-approximate what the probabilities are. But it's a fast check to see maybe this will give you the right approximation. So while performance was not the main, not what we were focused on during our implementation, we just wanted to show that our theory idiomatically embedded into a Haskell DSL. Just to show how each of the inference methods perform over a range of examples, what we have here is an n-way Ellsberg urn. So what happens is, the n-way Ellsberg urn, basically one ball has precise probability 1 on n, whereas the remaining balls share the rest of the mass imprecisely. So when we write up this program, this compiles to a binary decision diagram of order n, and we can see what happens to each of our inference methods when we run them. So the exact, as expected, because we have to perform 2 to the n minus 2 WMC passes, grows exponentially. The gradient grows linearly, but it's a fixed number of passes because, we just do the same number of passes no matter the balls, and this will eventually find the solution. So we have a very simple solver, so in this case it only goes up to 9, but it's extremely simple solver, and with just slightly more complex solvers you can find the solutions pretty simply. For the symbolic instantiation, this also grows exponentially because we need some kind of exponentially growing corner search, but because we don't have to perform WMC pass every time, which ends up being the more expensive operation, this grows slower than the exact method. And then interval, of course, is fastest out of all three, but of course it only gives a sound approximation, not necessarily tight. So yeah, in summary, what we have is just a standard pipeline that follows very closely to precise probabilistic programming languages, which are discrete. So yeah, what we have is type level names track the dependence of the 19 choices and restore commutivity in our language, which is kind of required for probabilistic programs. And so these names are enforced by GHC, but erased at runtime. And then, the key insight is that probabilistic and 19 variables both compile to the same types of BDD variables. It's just a 19 variable is a BDD variable with weight left free until inference time. And then one single semi-ring parametric algorithm gives 4 different types of inference methods based on which semi-ring you choose to probe the actual program with. So yeah, we have many future directions. So yeah, we were looking at continuous distributions. We're looking at optimizations, which include kind of extensions of binary decision diagrams and variable order heuristics when building them. And then, of course, we want also like infinite dimensional 19 structures, but yeah, these are more complicated. In the paper, we have well more examples than just the simple Ellsberg and these dependence programs. We have conditioning, we have an imprecise multi-Hall problem, we have interval-valued Markov decision processes, and yeah, so we have the package again on Hackage if you want to check it out, and yeah, our implementation is here too. So, thank you.
Okay, we're already past 5. Are there any questions from the audience? If not, let's thank our speaker again and see what Sam has to say.
Thanks, everyone. And thanks for a lot of great talks. And now, Dan. Oh, there we go. Dan, our Industrial Relations Chair, is going to say a brief word about our sponsors. Thanks.
Great. Do you want to say something about the Lottie School?
Yeah, sure. Yeah. Okay. Yeah, so Dan has worked really hard to recruit a lot of sponsors for ICFP to help make this happen. But I want to first mention one important sponsor, which is the Indiana University Luddy School of Informatics, Computing, and Engineering, where I work, and which provided significant fiscal support for this conference, making it possible to save significant amounts of money in holding this conference here at IU Indianapolis, and additionally provided me with lots of support. So I want to thank my colleagues at the Luddy School who contributed substantially to this event. So thank you.
Great, yeah, so I'm just gonna say a few words about our industry sponsors. We have a lot of returning sponsors this year, companies who've contributed again and again to make ICFP successful, and we're very grateful and happy to have them here. Every one of these organizations is working on ideas right now out of this community, things like types, proofs, effects, DSLs. These companies expand on the research, turning it into production infrastructures, and they're hiring, so. So first, Amazon, AWS, our environment sponsor this year. Everyone knows AWS as cloud, but fewer people may know that Amazon's automated reasoning group is one of the biggest concentrations of formal methods practitioners in industry. Cedar, their open source authorization language, has a formal model built in Lean with proofs that its components satisfy the safety and security properties that they care about, and which is checked against the production Rust implementation. They fund Daphne. They built Connie, a model checker for Rust. And if you prove things about programs for a living, you should know that they run an open call for proposals in automated reasoning. I'm actually just going to go through all of them, and we can applaud at the end. So, Jane Street is a platinum sponsor this year and also a major PLMW sponsor. They probably need no introduction for this room, given how many of you probably have interviewed there and definitely are wearing their shirts. Their trading business runs on OCaml, and last year they took the compiler branch they'd been developing internally for years, gave it a name and a logo, and shipped it to the rest of us as OxCaml. So unbox types, modes, stack allocation, correct by construction, multi-core, and of course, OCaml's type inference. Bloomberg is our other platinum sponsor. They use OCaml running in the terminal in their derivatives risk management application. If you've ever compiled OCaml to JavaScript, you're relying on Bloomberg. They also did BuckleScript that came out of their team, and the whole rescript and reason lineage that follows from it. Ahrefs is a silver sponsor this year. They crawl the entire web for search and marketing intelligence. I think the number they throw around is 25 petabytes. And they use OCaml to do it with Melange and ReasonML across the front end. They're a member of the OCaml Software Foundation, and they put work into OPAM. They've also started a grant program to fund projects in the OCaml ecosystem. So if you maintain an OCaml library, find them, talk to them. Galwa is a bronze sponsor this year. They've been building high assurance software for like 20 plus years, and most of it is in Haskell. Cryptal, SAW, Crucible. They also worked with Amazon to prove the correctness of the HMAC implementation in S2N, Amazon's TLS library. So, industry sponsors working together. We have two startup sponsors. Harmonic, they build Aristotle, which emits lean proofs. A verifier can check line by line rather than just, good sounding prose. They achieved formally verified solutions to 5 of the 6 problems at the 2025 International Mathematics Olympiad, which is a gold medal score. So basically, that means that a proof assistant is now the central technical asset of the company, and investors are definitely taking note. They've been doing well. And lastly, Nectri, which I should say I'm the CEO of Nectri, so whatever I say you can take with a grain of salt. We build a non-Turing complete DSL for AI agents, where the things an agent can and can't do are declared at compile time instead of filtered at runtime. So it compiles to Urweb, which is a language created by Adam Chapala, my co-founder, who I'm sure many of you are familiar with. And that's it. They were a big part of making ICFP happen, so please go talk to them, and if we could thank them now.
Thanks, and thanks to Dan, who's put in a ton of work as Industrial Relations Chair for several years now for ICFP. So now we have our reception, which is right out there. You can find drinks if you get a drink ticket, depending on what kind of drinks you're looking for. Some of them require tickets. And appetizers, and you can visit our sponsor booths, and you can also check out the student research contest posters that are out in the hallway. So enjoy the reception, and I will see all of you tomorrow morning for our next keynote.